How did atoms suddenly form from nothing? Everything in the universe, including our own existence, is made up of atoms. These tiny particles are the basic building blocks of everything we see around us. But have you ever wondered where atoms originally came from? Could the entire universe somehow be like one giant atom? And how do electrons keep moving around the nucleus without slowing down? Join us as we unravel the mind-boggling story of how atoms came into being from the void. The Big Bang is one of the most important ideas in science, explaining how the universe began. Imagine everything in the universe, every star, planet, and galaxy, being packed into one tiny, incredibly hot and dense point. Around 13.8 billion years ago, this point suddenly exploded, sending everything outward in all directions. This event is known as the Big Bang, and it marks the beginning of time itself. In the moments after the Big Bang, the universe was incredibly hot. It was like a giant glowing ball of energy and particles. In fact, it was so hot that atoms couldn't even form yet. Instead, the universe was filled with a soup of subatomic particles, like protons, neutrons, and electrons, all racing around at incredibly high speeds. Over time, as the universe expanded and cooled down, these particles began to slow down and combine, forming the first simple atoms, like hydrogen and helium. As the universe continued to grow, gravity started to pull these atoms together, forming the first stars. These stars were massive, burning bright and hot, and they formed clusters that eventually grew into galaxies. Galaxies are massive collections of stars, gas, dust, and other cosmic material, and they spread out across the universe like islands in a vast ocean of space. The aftermath of the Big Bang is still unfolding today. The universe is still expanding, meaning that galaxies are slowly moving farther away from each other. This discovery was made by astronomers in the 1920s, and it's one of the most surprising things about the Big Bang. It's like every galaxy is moving away from us, like a balloon being blown up. This idea has led scientists to think about what the future of the universe might hold. Will it keep expanding forever, or will it eventually slow down and collapse in on itself? No one knows for sure, but it's one of the great mysteries of modern science. The aftermath of the Big Bang didn't just shape the universe physically, but it also set the stage for the formation of the things we see around us. Stars and galaxies eventually gave birth to planets, including Earth. The elements that formed in stars created the building blocks of life, allowing life to emerge on planets like ours. In a way, the Big Bang not only created the universe, but it also gave rise to everything that makes our existence possible. Through the study of the Big Bang, scientists have learned a lot about how the universe began and how it continues to evolve. The evidence is all around us, from the faint glow of leftover light from the Big Bang, called the cosmic microwave background radiation, to the way galaxies move apart from each other. These clues help us piece together the story of the universe's birth, its growth, and its ongoing journey through time. The origins of the universe have been a topic of fascination and debate for centuries, but science has uncovered a remarkable theory that helps explain how everything we know began. This theory is known as the Big Bang theory, and it offers a breathtaking insight into the birth of the cosmos. Let's break it down in simpler words and elaborate on how the universe started from a tiny, extremely hot and dense point. Imagine everything in the universe, every galaxy, star, planet, and even the empty space between them, was once crammed into a single, incredibly tiny point. This point was so small that it defies our imagination. It's difficult for us to comprehend how something as vast as the entire universe could fit into something so minuscule. However, this is where the story begins. Before the universe began, there was no space as we understand it. Time itself didn't exist either. In other words, there was no before the Big Bang because time started with the Big Bang. Everything, space, time, and matter was packed into that minuscule point. It was so hot and dense that it was like the entire universe was squeezed into an infinitesimally small space. Around 13.8 billion years ago, this tiny, dense point began to rapidly expand. The term Big Bang refers to this dramatic event, the expansion from an incredibly hot, small, and dense state to what we observe today. It wasn't an explosion in the way we usually think of it, like a bomb going off. Instead, it was more like space itself began to stretch out, carrying everything in it. This expansion happened incredibly fast, much faster than the speed of light itself. It's called inflation in scientific terms. In the first few moments after the Big Bang, the universe was incredibly hot, much hotter than anything we could experience today. Imagine temperatures so high that even atoms couldn't form. The universe was filled with a hot, glowing soup of particles. These particles were too energetic to stick together, but as the universe cooled down, they began to bond, forming the simplest elements like hydrogen and helium. As the universe continued to expand, it also began to cool. Within the first few minutes, the temperature dropped enough for atomic nuclei to form. These nuclei, mainly hydrogen and helium, came together to create the building blocks for stars and galaxies. For the first few 100,000 years, the universe was a foggy, glowing mass of hot particles and radiation, and no light could travel freely. This period is called the era of recombination. However, as the universe continued to expand and cool, it eventually became transparent enough for light to travel. This moment marked the birth of the cosmic microwave background radiation, which we can still detect today with special instruments. This radiation is like a snapshot of the universe when it was only about 380,000 years old, providing a glimpse into its early days. Once the universe had cooled enough to allow light to travel, the next big step was the formation of galaxies and stars. As the tiny particles and gas clumped together under the force of gravity, they began to form large clouds of gas. These gas clouds eventually collapsed inward, forming stars. These stars became the heart of galaxies, and these galaxies started to group together to form even larger cosmic structures. In these early galaxies, stars were often much larger and hotter than the ones we see today. These stars lived short lives and exploded in massive events known as supernovae. When these stars exploded, they scattered heavy elements like carbon, oxygen, and iron throughout the universe. These elements became the building blocks for new stars, planets, and even life. Even today, the universe is still expanding. This was one of the most surprising discoveries about the universe. Scientists observed that galaxies were moving away from each other, and the farther a galaxy is, the faster it is moving away. This is evidence that the universe is still stretching, just like it was in the beginning. This ongoing expansion doesn't mean that galaxies are flying apart within space. Rather, space itself is stretching, and everything in it is moving farther apart. The analogy often used is that of a balloon. Imagine that the universe is the surface of a balloon, and the galaxies are like little dots on it. As the balloon inflates, the dots move farther apart. Similarly, as the universe expands, galaxies move farther apart from each other. While we can observe a lot about the universe, there is still much we don't understand. Two mysterious forces, dark matter and dark energy, play crucial roles in the universe's expansion. These forces make up a large portion of the universe's mass and energy, but they don't interact with light, making them invisible to us. We can only detect their effects on galaxies and other cosmic structures. Dark matter is believed to be responsible for the way galaxies rotate. Without dark matter, galaxies would fly apart because they don't have enough visible matter to hold them together. Dark energy, on the other hand, seems to be causing the universe's expansion to accelerate. Scientists aren't entirely sure what these forces are, but they are essential to our understanding of the universe. The universe is made up of billions of galaxies, each containing billions or even trillions of stars. Our own galaxy, the Milky Way, is just one among many. Over the course of billions of years, galaxies collided and merged, creating the cosmic landscape we see today. This constant process of formation, growth, and destruction is what shapes the universe and gives it the incredible diversity of stars, planets, and other objects we observe. One of the most intriguing aspects of the universe is its vastness. Even though the universe is expanding, the distances between objects like galaxies are so immense that we can barely comprehend them. The Milky Way itself is over 100,000 light-years wide, and light travels at about 186,000 miles per second. Yet, even at that incredible speed, it would take light more than 100,000 years to cross our galaxy. While the universe continues to expand, scientists also wonder about its ultimate fate. Some theories suggest that the universe could keep expanding forever, growing colder and emptier over time. Others propose that it could eventually slow down and collapse in on itself, in a process known as the Big Crunch. There's also the possibility of a Big Rip, where the expansion of the universe accelerates to the point where everything is torn apart. As of now, we don't have a definitive answer about how the universe will end. However, the story of its beginning, from an infinitesimally small, hot and dense point to the vast cosmos we observe today, is one of the most remarkable tales in science. The Big Bang theory offers a fascinating explanation of how the universe came into being, beginning from a single tiny point. From that moment of intense heat and density, the universe has been expanding and evolving, giving rise to stars, galaxies, and everything we see around us. Before atoms, before light, before even space and time as we know them, there was nothing. Or at least that's how we perceive it. But what does nothing really mean? In the world of physics, nothing isn't truly empty. Instead, it is a strange, chaotic state where virtual particles flicker in and out of existence, where energy roams without form, and where the laws of quantum mechanics reign supreme. So how did atoms, the very building blocks of matter, emerge from this seemingly endless void? To answer this, we need to journey back to the very beginning of everything, the birth of the universe itself. Our best scientific explanation for the origin of the universe is the Big Bang theory. This theory suggests that the universe began as an unimaginably tiny, hot, and dense singularity, a single point where all the energy and matter that would ever exist was concentrated. Then, in a fraction of a second, this singularity expanded with incredible force, setting the stage for everything that would follow. But what if the universe was born from a single point? Where did that point come from? And how could anything exist before time itself began? The answers lie in the strange world of quantum physics. In classical physics, nothing means empty space, complete and total emptiness. But in quantum mechanics, nothingness is never truly empty. Instead, it is filled with quantum fluctuations, tiny, unpredictable changes in energy that occur even in a vacuum. These fluctuations can create temporary particles that pop into existence and then vanish almost instantly. However, if a large enough fluctuation were to occur, it could trigger an event like the Big Bang, creating a vast amount of energy that rapidly expands into a universe. In other words, the universe may have emerged from a quantum fluctuation within an otherwise empty vacuum. Once the universe burst into existence, it wasn't filled with stars, planets, or atoms. Instead, it was an unimaginable storm of energy, a hot and chaotic plasma where particles constantly collided at extreme speeds. In these early moments, temperatures were so high that even basic atomic structures couldn't form. Particles simply smashed into each other and broke apart again. But as the universe expanded, it began to cool. And with cooling came the opportunity for something remarkable: the birth of atoms. As the universe cooled, energy transformed into matter. This transformation follows Einstein's famous equation, E = mc2, which tells us that energy and matter are interchangeable. As energy levels dropped, tiny subatomic particles, protons, neutrons, and electrons, began to take shape. Protons and neutrons formed first, coming together in small clusters due to the strong nuclear force, one of the four fundamental forces of nature. Electrons, which are much lighter, remained separate at first, zipping around in the chaotic early universe. At this stage, the universe was still too hot for these particles to form stable atoms. The intense energy kept tearing apart anything that tried to bond together. About 3 minutes after the Big Bang, the universe had cooled enough for nucleosynthesis to begin. This process allowed protons and neutrons to come together and form the first atomic nuclei. The first atoms to form were hydrogen and helium, the simplest elements in the universe. Hydrogen, consisting of just one proton and one electron, was by far the most abundant. Helium, with 2 protons and 2 neutrons, was the next most common. Small traces of lithium also formed, but even though their nuclei had formed, these atoms weren't complete yet. The universe was still too energetic, and free electrons were constantly being scattered by high-energy radiation. This prevented atoms from fully stabilizing. It took 380,000 years after the Big Bang for the universe to cool enough for atoms to truly come into existence. This event, known as the era of recombination, was a turning point. For the first time, electrons could settle into orbits around atomic nuclei without being constantly knocked away by high-energy photons, particles of light. This meant that actual, stable hydrogen and helium atoms could finally exist in large numbers. With atoms in place, something else extraordinary happened. The universe became transparent. Before recombination, the universe was a dense, foggy soup of free electrons that scattered light in all directions. But once electrons bonded with nuclei to form stable atoms, light was able to travel freely through space. This light is still visible today as the cosmic microwave background, CMB, a faint glow that scientists can detect in every direction, offering a glimpse into the universe's earliest days. Even though the first atoms had formed, the universe was still mostly an empty, dark expanse filled with hydrogen and helium gas. But gravity would soon change that. Over millions of years, tiny fluctuations in the density of gas clouds caused certain regions to become slightly denser than others. These denser areas pulled in more and more gas through gravity, growing larger over time. Eventually, the pressure and temperature inside these clouds became so intense that nuclear fusion began, the process that powers stars. Inside these first stars, hydrogen atoms were fused together to create heavier elements like carbon, oxygen, and even iron. These elements, forged in the hearts of stars, would later become the building blocks for planets, life, and everything we see today. If the universe could emerge from nothing once, could it happen again? Some theories suggest that our universe is just one of many in a multiverse, where new universes are constantly being created through quantum fluctuations. Others propose that the universe goes through endless cycles of expansion and collapse, with each cycle sparking the birth of a new cosmos. Whatever the answer, one thing is clear: the fact that atoms exist at all is nothing short of miraculous. From the emptiness of a quantum vacuum to the complex structures of galaxies, stars, and even life itself, the journey of atoms is one of the greatest stories ever told. The creation of atoms from nothingness is a testament to the power of nature's laws and the incredible transformations that can occur under extreme conditions. It took billions of years for the universe to evolve from a void of energy to the rich and complex cosmos we see today. And yet, even now, scientists are still trying to fully understand how something as fundamental as matter can emerge from nothing. Could there be deeper, hidden laws of physics we have yet to discover? Could the universe itself be part of a much larger, even grander reality? Quantum fluctuations are the result of one of the most fundamental principles in physics, Heisenberg's uncertainty principle. This principle states that at the smallest scales of reality, it is impossible to determine both the energy and time of a particle with absolute precision. Because of this, tiny particles and energy waves constantly appear and vanish in a restless dance of creation and destruction. Even in a complete vacuum, where no matter exists, these fluctuations still occur. Virtual particles, tiny, short-lived bits of energy, pop in and out of existence for fractions of a second before disappearing again. These fluctuations are not just theoretical ideas. Scientists have observed their effects in experiments. They are the reason why atoms do not collapse and why certain particles behave in ways that cannot be explained using classical physics. Before the Big Bang, these quantum fluctuations were everywhere. But at some point, something extraordinary happened, an event so powerful that it transformed these tiny ripples into the seeds of our universe. Scientists believe that a rapid expansion called cosmic inflation played a key role. During inflation, the universe expanded at an incomprehensible speed, stretching quantum fluctuations across vast distances. These tiny fluctuations, once confined to microscopic scales, were now amplified, creating density differences in the fabric of space itself. As the universe cooled, these variations in energy became the blueprint for everything that would follow. The slightly denser regions of space attracted more energy, forming the first building blocks of matter. In this way, quantum fluctuations, once mere flickers of uncertainty, became the foundation for galaxies, stars, and planets. Within the first microseconds of the universe's existence, the extreme energy started solidifying into the most fundamental building blocks of matter. These included quarks, the tiny particles that would later combine to form protons and neutrons; leptons, which include electrons, the particles that orbit atomic nuclei, gluons, which acted as the glue that held quarks together. At this stage, the universe was still a hot, dense plasma with particles colliding at incredible speeds. However, as it cooled further, something remarkable happened. Quarks combined to form protons and neutrons, the essential components of atomic nuclei. Around 380,000 years after the Big Bang, the universe had cooled enough for protons and neutrons to capture electrons, forming the first stable atoms. This process is known as recombination. The most common element to form was hydrogen, followed by helium and a small amount of lithium. At this point, the universe transformed from a chaotic, energetic soup into something more structured. For the first time, light could travel freely through space, leading to the release of what scientists call the cosmic microwave background radiation, a faint glow of energy that still exists today, serving as a snapshot of the early universe. While the formation of atoms was a crucial step, the universe was still far from what we see today. These early atoms were spread out across space, floating in vast clouds of gas. Over millions of years, gravity started pulling these atoms together, forming massive clumps. In some regions, the force of gravity was so strong that it squeezed atoms closer and closer, causing them to heat up and ignite nuclear fusion. This was the birth of the first stars. Inside these early stars, nuclear reactions fused hydrogen and helium atoms into heavier elements like carbon, oxygen, and iron, the very elements that make up planets and even life itself. When these stars reach the end of their lives, they explode as supernovae, scattering these elements across space. Over billions of years, this cosmic dust gathered into new stars, planets, and eventually, the Earth itself. It is mind-blowing to think that everything around us, from the air we breathe to the stars we see in the sky, can be traced back to tiny quantum fluctuations in the earliest moments of the universe. These fluctuations, initially random and unpredictable, laid the foundation for galaxies, planets, and life itself. Without them, the universe might have remained a smooth, featureless expanse of energy, never forming the complex structures we see today. It was the slight imbalances created by quantum fluctuations that allowed matter to clump together, leading to everything we know and experience. The story of the universe is a tale of transformation, of energy turning into matter, of simple atoms forming complex structures, and of the tiniest fluctuations shaping the grandest cosmic landscapes. Quantum fluctuations, once thought to be random noise, played a crucial role in this incredible process. Even today, quantum mechanics continues to challenge our understanding of reality. It tells us that at the most fundamental level, everything is uncertain. Yet this uncertainty led to the formation of something as vast and magnificent as the universe. Imagine a world where objects can suddenly pop in and out of existence, where something can be in two places at the same time, and where things behave in ways that completely defy common sense. This is not science fiction. This is the bizarre and fascinating reality of quantum mechanics, a branch of physics that describes how the tiniest building blocks of our universe behave. Unlike the world we experience daily, where objects follow predictable paths and rules, the quantum world is unpredictable, mysterious, and often downright strange. In this microscopic universe, particles, the tiny components that make up atoms, do not always behave like solid objects. Instead, they act like waves of energy, constantly shifting, appearing, disappearing, and even existing in multiple places at once. How is this possible? How can something vanish and reappear? To truly understand this, we must take a journey into the quantum world and uncover some of its most mind-boggling mysteries. To understand quantum mechanics, we first need to look at the scale we are dealing with. Atoms, the tiny building blocks of everything, are already incredibly small, so small that millions of them could fit on the tip of a needle. But atoms themselves are made up of even smaller particles, electrons, protons, and neutrons. And if we go even further down, we find subatomic particles like quarks and photons, which behave in ways that defy logic. In the world of quantum mechanics, these tiny particles do not act like little marbles or specks of dust. Instead, they behave more like waves of energy that can move in mysterious and unpredictable ways. This idea is called wave-particle duality, meaning that particles can sometimes act like solid objects and other times like waves of pure energy. One of the strangest phenomena in quantum mechanics is the ability of particles to appear and disappear seemingly at random. This happens because of a concept called quantum fluctuations. Even in the emptiest vacuum, where we would expect absolute nothingness, tiny particles are constantly popping in and out of existence. These are called virtual particles, and they exist for only a fraction of a second before vanishing again. This might sound impossible, but experiments have proven that these tiny bursts of energy happen all the time. How does this work? According to quantum mechanics, empty space is not truly empty. It is filled with quantum fields, invisible energy fields that extend throughout the universe. These fields are always vibrating, and sometimes, just for a moment, they create tiny particles out of nowhere. These particles flicker into existence and then disappear before we can fully detect them. This strange effect has real consequences. Scientists believe that quantum fluctuations played a crucial role in shaping the early universe. In fact, without these particles appearing and disappearing, the universe as we know it might not exist. To understand just how strange quantum mechanics can be, let's explore a famous thought experiment by physicist Erwin Schrödinger. He imagined a scenario involving a cat inside a sealed box, along with a mechanism that releases poison based on the behavior of a tiny quantum particle. According to quantum mechanics, before we open the box to check, the cat is neither fully alive nor fully dead. It exists in both states at the same time. This is because the tiny particle controlling the poison follows quantum rules, meaning it can be in two states at once until it is observed. This bizarre idea, known as superposition, suggests that things in the quantum world exist in multiple states until they are measured or observed. While Schrödinger's cat is just a thought experiment, the underlying concept has been tested in real experiments with tiny particles. Scientists have observed electrons and photons behaving in multiple ways at once, only choosing a definite state when they are measured. Another strange and fascinating feature of the quantum world is quantum tunneling. In the classical world, if you throw a ball at a wall, it will hit the surface and stop. But in the quantum world, a particle has a chance of passing through the wall as if it were a ghost. This happens because in quantum mechanics, particles are not just tiny dots, they also behave like waves. These waves can extend beyond barriers, meaning there is a small probability that the particle can tunnel through and appear on the other side. Quantum tunneling is not just a theoretical idea, it is a real effect used in technology. Modern electronics, such as the transistors in your computer and smartphone, rely on quantum tunneling to function. Without it, much of modern technology would not exist. One of the most important and puzzling principles in quantum mechanics is Heisenberg's uncertainty principle. This principle states that there is a fundamental limit to how precisely we can measure certain properties of a particle. For example, if we try to measure the exact position of an electron, we lose information about its speed. If we measure its speed, we lose information about its position. This uncertainty is not due to faulty equipment. It is built into the nature of reality itself. This means that at the quantum level, the universe is not fixed and predictable like the world we see around us. Instead, it is a shifting, uncertain realm where things exist in probabilities rather than definite states. One of the strangest and most fascinating aspects of quantum mechanics is quantum entanglement. This occurs when two particles become mysteriously linked, so that no matter how far apart they are, a change to one instantly affects the other. If one particle is measured and found to be spinning in a certain direction, the other particle, no matter if it is across the universe, will instantly spin in the opposite direction. This happens faster than the speed of light, defying what we thought were the limits of physics. Albert Einstein famously called this phenomenon spooky action at a distance. Although it sounds impossible, entanglement has been repeatedly proven in experiments. Scientists are even exploring ways to use quantum entanglement for ultra-secure communication and even future quantum computers. While quantum mechanics might sound like a strange and confusing theory, it is already shaping the future. Scientists are working on quantum computers, which use quantum particles to process information in ways that classical computers never could. These computers have the potential to revolutionize everything from medicine to artificial intelligence. Quantum mechanics is also being explored for new energy technologies, ultra-secure encryption, and even the possibility of teleportation. While true teleportation of people remains in the realm of science fiction, researchers have already successfully teleported tiny particles using quantum entanglement. To understand quantum fluctuations, let's start with a basic idea. Empty space is not really empty. Even in what seems like a complete vacuum, where no air, light, or particles exist, there is still something happening. Quantum mechanics, the branch of physics that studies the tiniest building blocks of reality, tells us that space is filled with an invisible energy field called the quantum field. Quantum mechanics, the branch of physics that studies the tiniest building blocks of reality, tells us that space is filled with an invisible energy field called the quantum field. This field is never truly still. It constantly shifts and moves due to the unpredictable nature of quantum mechanics. A quantum fluctuation is a tiny, temporary change in energy that happens within this field. Imagine a calm pond of water. If you throw a stone into it, ripples will appear on the surface. These ripples represent small disturbances, just like quantum fluctuations are tiny disturbances in the energy field of space. The difference is that in quantum physics, these fluctuations happen spontaneously and without any external cause. They just pop in and out of existence on their own. At first glance, the idea that something can come from nothing might seem completely illogical. In our everyday world, objects don't just appear out of thin air. But in the quantum world, the rules are very different from what we experience on a daily basis. The key to understanding this lies in a fundamental principle of quantum mechanics called the Heisenberg uncertainty principle. This principle states that certain properties of particles, such as energy and time, cannot be measured exactly at the same time. Because of this uncertainty, for incredibly brief moments, energy can exist where there was none before. These small bursts of energy sometimes transform into pairs of particles, one of matter and one of antimatter, that exist for just a tiny fraction of a second before disappearing again. These virtual particles constantly appear and vanish, meaning that at the most fundamental level, space is never truly empty. Even in a vacuum, these particles flicker in and out of reality, making nothingness far more complicated than we once thought. Quantum fluctuations are not just a weird theoretical concept, they play a crucial role in shaping the universe as we know it. Here are a few ways in which these tiny energy blips have had a massive impact on reality. One of the most exciting ideas in cosmology is that the entire universe may have originated from a quantum fluctuation. Scientists believe that before the Big Bang, the universe was in a highly unstable quantum state. A tiny fluctuation in this state could have triggered the sudden explosion of energy that created the cosmos. This idea suggests that the universe did not need a pre-existing cause to begin. It could have simply emerged from the quantum vacuum due to the fundamental laws of physics. If this is true, then everything we see around us, from galaxies to planets to life itself, may have started as a tiny, fleeting energy blip. Quantum fluctuations are also responsible for shaping the structure of the universe. In the early moments after the Big Bang, tiny energy variations in the quantum field caused slight differences in density in the rapidly expanding universe. Over time, these small differences grew into large cosmic structures, forming the galaxies, stars, and planets we see today. Without these quantum fluctuations, the universe might have remained smooth and featureless, never developing the complexity we now observe. In a way, the entire cosmic web, the vast network of galaxies stretching across billions of light years, owes its existence to the unpredictable nature of quantum physics. Black holes are some of the most mysterious objects in the universe, but even they are influenced by quantum fluctuations. Stephen Hawking, one of the greatest physicists of all time, proposed that black holes slowly lose energy and shrink over time due to a process called Hawking radiation. According to this theory, pairs of virtual particles created by quantum fluctuations can sometimes be split apart at the edge of a black hole. One particle falls in, while the other escapes, causing the black hole to lose a tiny bit of mass. Over vast amounts of time, this slow loss of particles could eventually lead to the black hole's complete evaporation. You might be wondering, do quantum fluctuations have any effect on our daily lives? While they mostly operate on a scale that is too small for us to notice, they do play a role in certain real-world phenomena. One example is the stability of atoms. Quantum fluctuations help determine the behavior of subatomic particles, which in turn influence how atoms interact with each other. Without these fluctuations, the fundamental forces of nature might behave differently, and matter as we know it could not exist. Another fascinating example is quantum computers. These advanced machines take advantage of quantum fluctuations to process information in ways that traditional computers cannot. By harnessing the strange properties of quantum mechanics, scientists are developing computers that could one day revolutionize fields like cryptography, artificial intelligence, and scientific research. If tiny quantum fluctuations can create particles, could a much larger fluctuation create something as massive as an entirely new universe? Some physicists believe this is possible. There is a theory known as eternal inflation, which suggests that our universe is just one of many that have been created by quantum fluctuations in a constantly expanding cosmic space. In this view, new universes could be popping into existence all the time, each with different physical laws and properties. The idea that tiny bursts of energy can create matter from nothing is one of the most exciting concepts in modern science. Quantum fluctuations challenge our understanding of reality, showing us that the universe is far stranger and more mysterious than we ever imagined. These tiny, fleeting blips of energy have helped shape everything, from the smallest particles to the largest galaxies. They may have even played a role in the creation of the universe itself. While we still have much to learn about quantum physics, one thing is clear. The idea that something can come from nothing is not just a fantasy. It's a fundamental part of how our universe works. Atoms, the tiny building blocks of everything we see around us, owe their existence to a fascinating and delicate process that took place in the early universe. However, to truly understand how atoms came to be, we must first explore a key phenomenon: fluctuations. These tiny, seemingly random variations in energy and density played an essential role in shaping the universe and making the formation of atoms possible. During this early phase, the universe was like a boiling cauldron of energy, where particles constantly collided and transformed into different forms. However, the energy wasn't distributed perfectly evenly. Some regions had slightly more energy, while others had slightly less. These small differences or fluctuations might seem insignificant, but they were crucial to shaping the future of the universe. Fluctuations are best thought of as tiny ripples in the fabric of space, caused by natural variations in energy. These ripples existed due to a fundamental principle in physics known as quantum mechanics, which states that energy and matter are never perfectly uniform at the smallest scales. Even in what seems like empty space, tiny changes are always occurring. In the incredibly hot and dense early universe, these fluctuations were stretched and magnified as space expanded. Some regions became slightly denser than others, meaning they had more energy and matter. Over time, these small differences would set the stage for everything that followed, determining where galaxies, stars, and even atoms would form. As the universe continued to expand and cool, something incredible happened. Energy began transforming into matter. This process followed the famous equation E=mc2, formulated by Albert Einstein, which explains how energy can turn into mass. However, this transformation didn't happen smoothly or all at once. It depended heavily on the earlier fluctuations. In areas where the energy was slightly higher due to these variations, more particles could form. These denser regions became the first places where subatomic particles like quarks and gluons started to combine and form the building blocks of atoms. Within the first millionths of a second, quarks grouped together to form protons and neutrons, the core components of atomic nuclei. But the process didn't stop there. For atoms to fully form, protons and neutrons needed to capture electrons to create stable structures. However, in the hot early universe, free electrons were flying around at high speeds, making it impossible for them to join atomic nuclei. The entire cosmos was filled with a dense plasma-like state, where light couldn't travel freely because it was constantly bouncing off free electrons. After hundreds of thousands of years of cooling, the temperature of the universe finally dropped enough for electrons to slow down and become captured by atomic nuclei. This period is known as recombination, and it marked the true birth of the first atoms. With electrons now bound to nuclei, the universe became transparent to light for the first time, allowing radiation to travel freely. This light, known today as the cosmic microwave background, CMB, is still visible and serves as a snapshot of the early universe. The first atoms to form were the simplest ones, hydrogen and helium. These elements made up 99% of the universe's atomic content. Over time, gravity pulled these atoms together to form clouds of gas, which later gave birth to the first stars and galaxies. If the early universe had been perfectly uniform, without fluctuations, matter would have remained evenly spread out. There would have been no denser regions where gravity could begin pulling atoms together, and without that, no stars, planets, or galaxies would have formed. These tiny fluctuations acted like seeds, providing the small differences needed for gravity to work its magic. In regions where there was slightly more matter, the gravitational pull was stronger, attracting even more matter over time. This snowball effect led to the formation of stars, which then forged heavier elements like carbon, oxygen, and iron, the essential ingredients for life. The universe is often described in many different ways, from being vast and endless to being full of mystery and wonder. One way scientists and philosophers like to think about the universe is as a chaotic soup of energy and elementary particles. This idea paints a picture of a place filled with endless motion, tiny bits of matter, and powerful forces all mixing together in unpredictable ways. To understand this concept, let's break it down into parts. First, what are these elementary particles people talk about? These are the smallest pieces of matter we know of, things like electrons, protons, and neutrons. But even smaller than these are quarks and leptons, which are considered the building blocks of everything in the universe. These particles are so small that they can't be seen with the naked eye, or even with most microscopes. They exist in a world that's completely different from what we experience every day. In the universe, everything is made up of these tiny particles which are in constant motion. Picture a bustling city with cars, people, and buses all moving around in every direction. Now imagine that instead of cars and people, it's tiny particles that are moving around, and they don't follow any predictable patterns. This is what makes the universe feel chaotic. There are so many particles, and they are all interacting with each other in ways that we can't always predict. The way they move, collide, and change is constantly changing, making the universe a place of constant change and unpredictability. When we talk about energy in this context, it's like the fuel that keeps everything moving. Energy is what allows particles to exist and interact. It can be found in many forms: light, heat, motion, and even the very forces that hold matter together. Energy isn't something you can always see, but it's everywhere. It flows through everything, and it's the reason particles move, collide, and change. Without energy, nothing would happen in the universe. Imagine a giant pot of soup. The soup represents the universe, and the ingredients are the particles and energy. Just like how the ingredients of a soup are mixed together, in the universe, particles and energy are constantly interacting with each other. They are not neatly separated, but are instead all tangled together, creating a chaotic environment. Sometimes the ingredients blend together, creating something new. Other times they crash into each other, creating sparks or bursts of energy. This chaotic interaction is the driving force behind everything we see in the universe, from the stars and planets to the forces that shape galaxies and black holes. One of the most important ideas in this chaotic soup is that nothing is ever truly still. Particles are always moving. Even if something seems like it's standing still, like a rock or a planet, if we look closely enough, we'll see that everything is in motion. The atoms that make up the rock are vibrating, the particles inside them are moving, and even the rock itself is slowly drifting through space. The same is true for all the matter in the universe. Nothing is truly at rest. This constant motion is also tied to something called the uncertainty principle, a key idea in quantum physics. The uncertainty principle tells us that we can never know everything about a particle at once. For example, we might know where a particle is, but we can't be certain about how fast it's moving. Or we might know how fast it's moving, but we can't know its exact position. This is just one example of the chaos in the universe. Particles don't behave in simple, predictable ways like we might expect. The energy in the universe also comes in different forms. Some forms are visible to us, like light, which is a type of energy. Other forms are invisible, like gravitational energy or the energy stored in atoms. Even more mysterious are things like dark energy and dark matter, which make up most of the universe but are still not fully understood. Dark energy is thought to be responsible for the accelerating expansion of the universe, pushing galaxies further apart. Dark matter, on the other hand, helps explain why galaxies don't fly apart, even though they seem to be spinning too fast to stay together. These unseen forces add more layers of mystery and chaos to the universe. At an even smaller scale, the chaotic soup of particles and energy takes on even stranger qualities. In the quantum world, particles can behave like waves, or waves can behave like particles. They can appear in multiple places at once or suddenly vanish from one spot and reappear in another. This is where things get even more mind-boggling. In this strange world, the rules of classical physics no longer apply, and particles can seem to break the rules of space and time itself. This unpredictable, bizarre behavior only adds to the chaos of the universe. Now let's zoom out from the microscopic level to the larger scale of the universe. As these particles and energy interact, they form everything we see around us: stars, planets, galaxies, and even black holes. In fact, the largest structures in the universe, like galaxies and clusters of galaxies, are also formed by this same chaotic soup of energy and particles. Gravity, one of the fundamental forces in the universe, is what holds stars and planets together. But gravity itself is influenced by energy and particles in ways that are not always predictable. For example, black holes are regions of space where gravity is so strong that not even light can escape. They form when massive stars collapse and their energy and matter get squeezed into a tiny space. The intense gravity and energy in these regions can warp space and time itself, creating some of the most extreme and mysterious environments in the universe. Even on a grand scale, the universe is full of chaos. The expansion of the universe, for example, is not uniform. Some regions of space are expanding faster than others, and the universe itself is constantly changing in ways that are still not fully understood. The birth of stars and galaxies, the death of stars in supernova explosions, and the formation of black holes are all parts of this ongoing process of change. Over billions of years, the universe evolves, and the chaotic interactions between particles and energy continue to shape everything that exists. Despite all the chaos, there is an underlying order to the universe. The laws of physics like gravity, electromagnetism, and nuclear forces govern how particles behave and interact with each other. These laws give structure to the universe, but they also allow for the unpredictability and complexity that make the universe so fascinating. It's this delicate balance between order and chaos that makes the universe both predictable and mysterious at the same time. As the temperature fell, the energy was able to condense into tiny particles. First, quarks, which are the fundamental building blocks of matter, began to form. Quarks, however, couldn't exist on their own for long. They combined in pairs to create protons and neutrons, which are the building blocks of atoms. This happened in the first few minutes after the Big Bang. But temperature wasn't the only factor at play. Pressure also played a crucial role in shaping the early universe. As the universe expanded, the space between particles grew larger, but this expansion didn't happen uniformly. In some areas, the density of matter was higher than in others, causing some regions to experience higher pressures. These pressures helped to push particles together and facilitated the formation of new types of matter. During this period, the universe was filled with a dense soup of particles: quarks, electrons, photons, light particles, and neutrinos. The high temperature and pressure in the early universe caused constant collisions between these particles, resulting in new particles being created while others were destroyed. For example, in this early phase, particle-antiparticle pairs were created and annihilated almost instantly. This back-and-forth process continued until the universe had cooled sufficiently for more stable particles, like protons and neutrons, to remain intact. As the universe continued to cool over the next few minutes, the pressure from the expansion began to decrease, and this allowed the quarks to combine and form protons and neutrons more stably. This is when nucleosynthesis occurred, a process that formed the first atomic nuclei. In this phase, which happened about 3 minutes after the Big Bang, protons and neutrons combined to form the simplest nuclei: hydrogen, helium, and small traces of other light elements like lithium. At the same time, the temperature of the universe had dropped enough for electrons to form. These electrons then combine with the newly formed nuclei to create atoms. The pressure at this time was still relatively high compared to what we experience today, but it was nothing like it had been in the early moments after the Big Bang. As the pressure and temperature continued to fall, the universe entered a new phase of evolution. The formation of neutral atoms, especially hydrogen, allowed photons, light particles, to travel freely through space. The creation of atoms marked the beginning of a new era in the universe's history, the era of recombination. This era was significant because for the first time, the universe was filled with neutral atoms instead of charged particles. This was also the moment when the cosmic microwave background, CMB radiation, the faint glow we can still detect today, was released. Even though the universe had cooled and expanded over the first few 100,000 years, temperature and pressure continued to influence its evolution. As the universe continued to cool, matter began to clump together due to gravity, forming the first stars and galaxies. As stars formed, they created new, heavier elements through nuclear fusion, leading to the creation of the elements that make up planets and life as we know it. Throughout this process, temperature and pressure have remained fundamental in shaping the universe. Stars are born when the pressure from gravity compresses gas clouds so tightly that the temperature rises enough to trigger nuclear fusion, the process that powers stars. In the hearts of these stars, extreme temperatures and pressures enable the formation of even heavier elements, like carbon, oxygen, and iron, which are essential for life. In the earliest moments of the universe, everything was pure energy. There were no stars, planets, or galaxies. There were no atoms or particles like the ones we encounter every day. The entire universe was a dense, hot, and fiery ball of energy. Think of it like a super powerful, invisible furnace, but on a scale far larger than we could ever imagine. It was so hot that nothing could exist as solid matter. It was all energy. As the universe began to expand, it cooled. This cooling process took a very long time, millions and millions of years. As it cooled down, it started to change in dramatic ways. Energy slowly turned into matter. But how does that happen? When the universe was incredibly hot, it was made up of small particles of pure energy. The universe's cooling allowed these particles to combine in new ways. In the first few moments after the Big Bang, the temperature was so high that particles like protons and neutrons couldn't form. Instead, there were only subatomic particles called quarks. These quarks were like tiny building blocks of matter, but they were too hot and energetic to stay together in anything stable. As the universe expanded and cooled, these quarks began to stick together to form protons and neutrons. Protons are positively charged particles, while neutrons have no charge at all. These protons and neutrons then came together to form the nuclei of simple elements, like hydrogen and helium. This moment is called nucleosynthesis, and it happened when the universe was just a few minutes old. At this point, the universe was still a very strange place. It was filled with a hot soup of particles and radiation, all moving around at incredibly high speeds. There were no stars, no galaxies, and no planets yet. But this soup of particles was slowly cooling and beginning to form the basic building blocks for everything that would come later. This is where the process of energy turning into matter truly begins to take shape. As time passed, the universe continued to cool and expand. About 380,000 years after the Big Bang, the temperature dropped enough for electrons to join with protons and neutrons to form the first atoms. This was a crucial moment in the history of the universe. When these atoms formed, the universe suddenly became transparent. Before this, it had been opaque, like a foggy soup of particles, because light couldn't travel freely. But once atoms formed, light could finally travel through space. These first atoms were mostly hydrogen and helium, the two lightest elements. They were scattered across the universe, and for a long time nothing much happened. The universe was dark and quiet, and there were no stars yet. But these atoms were starting to gather together due to the force of gravity, which caused them to clump together. Over time, these clumps of hydrogen gas grew larger and denser. As these clumps continued to grow, they began to heat up. Eventually, the gas in these clumps became so hot and dense that it started to glow. These glowing clouds of gas are what we now call stars. The first stars were born from this process of cooling and gathering. The birth of the first stars marked the beginning of a new phase in the universe's history. Stars are incredibly important because they are the factories where all the heavier elements in the universe are created. Inside a star, hydrogen atoms fuse together to create helium. This process releases a huge amount of energy, which is why stars shine so brightly. As stars continue to burn, they eventually start to create heavier elements like carbon, oxygen, and iron. The stars themselves are constantly changing. They can live for millions or even billions of years before their energy starts to run out. When a star runs out of fuel, it can explode in a massive event called a supernova. During this explosion, the star releases a huge amount of energy, and the pressure causes it to create even heavier elements like gold, platinum, and uranium. These heavy elements are crucial because they are the building blocks for planets, rocks, and even life. After a star explodes, the elements it created are scattered throughout space. Over time, these elements gather together to form new stars, planets, and other objects. This process of stars creating elements and then exploding to scatter them into space is how the universe gradually became more complex. So the transformation from pure energy into matter was not an immediate change. It was a slow and gradual process that took billions of years. The early universe was a hot, dense ball of energy, and as it expanded and cooled, that energy transformed into matter. Atoms formed, stars were born, and these stars create heavier elements that would later form planets and other objects. Over time, the universe continued to cool, and everything we see today, from galaxies to planets to life itself, emerged from that first burst of energy. This process is what scientists call the cooling of the universe and the transformation from pure energy into matter. It's the story of how the universe went from being a hot, chaotic mess of energy to the complex, structured cosmos we see today. And while this story began billions of years ago, it's still unfolding in many ways. New stars are still being born, new galaxies are still forming, and the universe continues to evolve. One fascinating thing about the cooling of the universe is that it allows scientists to study the early moments of the universe. By looking at the oldest light we can see, something called the cosmic microwave background, CMB, scientists can learn about what the universe was like in its earliest moments, just after the Big Bang. This light is a remnant of that hot, dense time, and by studying it, we can learn more about how the universe began and how it continues to change. In a way, the cooling of the universe is still happening. The universe is still expanding, and as it gets larger, the space between galaxies continues to grow. The cooling process has slowed down dramatically since the Big Bang, but it's not over yet. As the universe expands and cools, it will continue to evolve, and who knows what new discoveries we will make as we look deeper into space. Albert Einstein's equation is one of the most famous formulas in science. It's often referred to as the energy-mass equivalence equation. While it might sound complex at first, it's actually a simple yet powerful way of understanding how energy and mass are connected. The equation itself states that energy is equal to mass times the speed of light squared. The speed of light is roughly 300,000 kilometers per second, so when you square this huge number, you get an extraordinarily large value. But what does this have to do with the birth of atoms? To understand that, we need to break down the equation and see how it relates to the very beginnings of matter itself. In simple terms, Einstein's equation tells us that mass and energy are interchangeable. They're not separate, independent things, but are actually two forms of the same thing. If you have an object with mass, you can think of it as having a hidden store of energy, just waiting to be released. Likewise, energy can be converted into mass. This idea is incredibly important when we think about the birth of atoms, because the process of creating atoms and the universe itself starts with energy being converted into mass. To understand how Einstein's equation connects to the creation of atoms, we have to go back to the very beginning of the universe, right after the Big Bang. Around 13.8 billion years ago, the universe began as a tiny, incredibly hot and dense point. In those first moments, the universe was pure energy. There were no atoms, no stars, no planets, just an explosion of energy. This energy was so intense that it began to turn into mass, which would later form the building blocks of all matter. The process by which energy transformed into mass and vice versa happened incredibly fast. As the universe expanded and cooled, some of the energy started to condense into tiny particles, such as protons, neutrons, and electrons. the building blocks of atoms. Think of it like this. If you could imagine energy as a kind of invisible material, when this energy cooled down, it could freeze into little bits of mass, protons, neutrons, and electrons. These particles, held together by forces, eventually formed the first atoms. Here's where Einstein's equation comes in. The energy from the Big Bang, as the universe expanded and cooled, was being turned into mass. This mass wasn't immediately formed into atoms like we see today, but it eventually came together to form the simplest atoms, hydrogen and helium. These are the building blocks of everything we see in the universe today. When energy from the Big Bang converted into mass, it didn't just form individual particles. It also gave birth to the forces that hold matter together. The electromagnetic force, the strong nuclear force, and the weak nuclear force all played roles in how these particles combined and interacted. Here's where Einstein's equation comes in. The energy from the Big Bang, as the universe expanded and cooled, was being turned into mass. This mass wasn't immediately formed into atoms like we see today, but it eventually came together to form the simplest atoms, hydrogen and helium. These are the building blocks of everything we see in the universe today. When energy from the Big Bang converted into mass, it didn't just form individual particles. It also gave birth to the forces that hold matter together. The electromagnetic force, the strong nuclear force, and the weak nuclear force all played roles in how these particles combined and interacted. This led to the formation of atomic nuclei, protons and neutrons sticking together to form the center of atoms. However, the universe was still too hot for atoms to form directly at first. Instead, the protons and neutrons collided and fused together to create nuclei of hydrogen, helium, and trace amounts of other elements. It wasn't until the universe cooled down enough that electrons could slow down and join with these nuclei to form neutral atoms. This process is called recombination, and it happened roughly 380,000 years after the Big Bang. You might wonder why Einstein used the speed of light in his equation. The reason is that the speed of light is a constant that relates to how fast energy and mass can interact. Since the speed of light is so large, squaring it makes the equation incredibly powerful. Even a small amount of mass can be converted into a huge amount of energy. This concept of energy-mass equivalence helps scientists understand how processes like nuclear fusion in stars and the creation of particles in the early universe work. In the early universe, particles didn't just form one by one. They were constantly colliding and transforming, changing between different types of energy and mass. This high-energy environment was necessary for the creation of atoms. When energy was released during these interactions, it often took the form of radiation, which was light and heat that traveled incredibly fast, at the speed of light. One of the most direct ways that energy turned into mass in the early universe was through nuclear fusion. This is the process that powers the sun today. When atoms are fused together, energy is released, and new elements are created. In the early universe, energy from the Big Bang caused particles to move so fast and collide so violently that they fused together. This fusion created the first atomic nuclei. For instance, hydrogen nuclei, protons, could fuse to form helium nuclei. This process, known as primordial nucleosynthesis, happened during the first few minutes after the Big Bang, when the universe was still very hot and dense. The particles were moving so fast that their energy, as described by Einstein's equation, was enough to overcome the repulsive forces between them, causing them to merge and create heavier elements. The energy released in these nuclear reactions was immense, and it helped create the mass that would eventually form the stars, galaxies, and eventually the atoms that make up everything in the universe. Today, atoms are the basic building blocks of matter, and they make up everything around us, from the air we breathe to the stars in the sky. Each atom is made of a nucleus, consisting of protons and neutrons, and electrons that orbit around the nucleus. The properties of these atoms depend on the interactions between their particles, which were all shaped by the energy that existed in the early universe. The question of how pure energy can be transformed into matter is one of the most profound mysteries of the universe. It lies at the heart of some of the most mind-boggling theories in physics and cosmology. The transformation of pure energy into matter is not just an abstract concept. It is a process that played a vital role in the formation of the universe itself. In the earliest moments of the universe, energy began to take shape in the form of particles. The very first particles to appear were quarks and leptons. These are the most basic building blocks of matter. Quarks combine to form protons and neutrons, the particles that make up the nuclei of atoms, while leptons include electrons. The process of transforming energy into matter was not instant. It took time for these elementary particles to form. In the first few microseconds after the Big Bang, the universe was so hot that particles couldn't stick together to form matter. Instead, they existed as a high-energy plasma, bouncing around at incredibly high speeds. As the universe cooled, conditions became right for quarks to combine into protons and neutrons, and for electrons to form around these particles. This transformation of pure energy into matter was an essential step in the formation of atoms, and ultimately, everything in the universe. However, the process didn't stop there. The early universe continued to cool, and over time the particles began to interact in more complex ways. For the transformation of energy into matter to occur, fundamental forces played a crucial role. These forces are the invisible rules that govern how particles interact with each other. The most important forces during the early universe were the strong nuclear force and the electromagnetic force. Strong nuclear force. This force is responsible for holding the quarks together to form protons and neutrons. It is one of the strongest forces in nature, but only operates over incredibly short distances. When the universe was in its earliest moments, the strong force was powerful enough to allow quarks to stick together and form protons and neutrons. Electromagnetic force. Once the universe cooled enough, the electromagnetic force played a critical role in allowing electrons to come together with protons to form hydrogen atoms. Electrons are negatively charged, and protons are positively charged, so they naturally attract each other and combine to form stable atoms. While the process of turning pure energy into matter during the Big Bang is relatively well understood, there are still many mysteries that remain. One of the biggest questions in modern cosmology is the nature of dark matter and dark energy. Dark matter is a form of matter that does not emit, absorb, or reflect light, making it invisible to our current instruments. However, scientists believe that dark matter makes up about 27% of the universe. It interacts with regular matter through gravity, which allows scientists to detect its presence indirectly. But how dark matter was formed from pure energy remains one of the great mysteries of modern science. Even more mysterious than dark matter is dark energy, a force that seems to be driving the accelerated expansion of the universe. Dark energy makes up about 68% of the universe, but scientists have very little understanding of how it works. Some theories suggest that dark energy could be linked to the energy that was present in the early universe, though this is still a topic of much debate. The process of transforming pure energy into matter didn't just stop with the creation of hydrogen atoms. Over billions of years, the universe continued to evolve. Stars formed from clouds of gas, and inside those stars, nuclear fusion took place. During fusion, smaller elements like hydrogen and helium fused to form heavier elements, releasing massive amounts of energy. These elements eventually spread out into space, creating new stars, planets, and galaxies. Our entire universe is a product of this transformation of energy into matter. From the first moments of the Big Bang, pure energy slowly transformed into the complex and diverse matter that makes up everything we see today, from the stars in the sky to the atoms in our bodies. The process of converting radiation into particles such as protons, neutrons, and electrons is a fascinating phenomenon that takes place in various scientific and cosmic environments. To break it down, let's first understand what radiation is and how it can lead to the creation of these fundamental particles. Radiation is essentially energy that travels in the form of waves or particles. It can come from many sources such as the sun, radioactive materials, or even cosmic rays from outer space. Radiation can take different forms: light, heat, X-rays, gamma rays, or even highly energetic particles like cosmic rays. Now, the key idea here is that this energy can sometimes transform into tiny particles, which are the building blocks of matter. Protons, these are positively charged particles found in the nucleus of every atom. They play a crucial role in determining the identity of elements. For example, a hydrogen atom has just one proton in its nucleus, while helium has two. Neutrons. Neutrons are neutral particles that also reside in the nucleus of atoms. They don't have any charge, but they contribute to the atom's mass and help stabilize the nucleus. Electrons. These are negatively charged particles that orbit around the nucleus of atoms. They are much lighter than protons and neutrons and play a vital role in chemical reactions and electricity. So how does radiation lead to the creation of these particles? The process often begins with high-energy radiation, such as gamma rays or cosmic rays, interacting with matter. When these high-energy particles or waves collide with atoms, they can break apart or cause a transformation of energy into different forms, including subatomic particles like protons, neutrons, and electrons. One of the key processes that explain this conversion is called pair production. This happens when a very energetic photon, a particle of light or radiation, interacts with a strong electromagnetic field, often near the nucleus of an atom. When the photon's energy is high enough, it can transform into a particle-antiparticle pair, usually an electron and a positron, the antimatter counterpart of an electron. The creation of these particles happens because the energy from the photon is converted into mass, thanks to Albert Einstein's famous equation, which shows how energy and mass are interchangeable. Another way radiation can lead to the creation of particles is through high-energy collisions. For example, when cosmic rays, which are high-energy particles from space, strike the Earth's atmosphere, they can collide with atoms in the air, breaking apart those atoms and creating new particles. This is how showers of secondary particles, including protons, neutrons, and electrons, are generated. In particle accelerators, scientists deliberately accelerate particles to nearly the speed of light and make them collide with other particles, causing these collisions to produce new particles. In nuclear reactions, such as those occurring in the sun or in nuclear reactors, radiation can also play a role in the creation of particles. During nuclear fission or fusion, large atomic nuclei break apart or combine, releasing massive amounts of energy in the form of radiation. This radiation can cause further reactions that produce subatomic particles like protons and neutrons. For example, when a neutron hits a nucleus in a reactor, it can cause the nucleus to split and release additional particles and radiation. This conversion of radiation into particles isn't just something that happens in labs or reactors. In fact, it's happening all around us, especially in outer space. Stars, including our sun, produce enormous amounts of radiation, much of which is high-energy gamma rays and X-rays. These rays can interact with particles in space, creating new particles in a process that has helped shape the universe as we know it. The same process also happens in the mysterious realm of black holes. When matter falls into a black hole, it is subjected to intense radiation, and this can trigger the production of various particles. Even in the vast, empty regions between stars, cosmic radiation is constantly at work, creating new particles and influencing the behavior of galaxies. Everything around us, the air we breathe, the ground beneath our feet, the stars in the night sky, was once forged in the heart of the universe through an incredible process called nucleosynthesis. This is the method by which atoms are created, beginning with the earliest moments of the universe and continuing inside stars, during massive cosmic explosions, and even in deep space. Imagine the universe at the very beginning, a hot, dense, and chaotic place. This was the time of the Big Bang, an event that kick-started everything. In the first few minutes after the Big Bang, temperatures were unimaginably high, and tiny particles called nucleons, protons and neutrons, were moving around at incredible speeds, constantly colliding and fusing together. During this brief but critical period, known as Big Bang nucleosynthesis, the first atomic nuclei were formed. However, because the universe was expanding rapidly, it cooled down quickly. After about 20 minutes, it became too cold for further nuclear reactions to take place. By this time, almost all the matter in the universe was in the form of hydrogen and helium, the two lightest and most abundant elements. A tiny amount of lithium and deuterium, a heavier form of hydrogen, also formed. This means that at the beginning of time, the universe was mostly just a vast sea of hydrogen and helium, with only faint traces of other elements. So where did all the other elements, like oxygen, carbon, gold, and iron, come from? The answer lies in the life and death of stars. Stars are not just bright lights in the sky. They are giant, natural nuclear reactors that create new elements deep within their fiery cores. This process is called stellar nucleosynthesis. A star forms when a huge cloud of hydrogen gas collapses under gravity, igniting nuclear fusion in its core. This fusion process smashes hydrogen atoms together, forming helium and releasing enormous amounts of energy. This is what makes stars shine. As stars grow older and hotter, they start fusing helium into heavier elements like carbon, oxygen, neon, and silicon. In the most massive stars, this process continues all the way up to iron and nickel. However, something interesting happens at this stage. Once a star produces iron, fusion can no longer release energy. Instead, the star becomes unstable, and for the biggest ones, this leads to one of the most spectacular events in the universe, a supernova explosion. A supernova is an enormous stellar explosion that occurs when a massive star reaches the end of its life. During this explosion, the star scatters all the elements it created into space, enriching the universe with a wide variety of heavier elements. But that's not all. Supernovae also create new elements through intense nuclear reactions. In the split-second chaos of the explosion, atomic nuclei smash together in ways that normally wouldn't happen inside a star. This leads to the formation of even heavier elements, such as gold, uranium, and platinum. There's another special process at play here, known as the R process, rapid neutron capture process. This happens when atoms absorb multiple neutrons in a short period of time, allowing them to grow into much heavier elements. Supernovae are one of the key locations where this occurs. Recent discoveries have revealed another cosmic event responsible for making heavy elements: neutron star mergers. Neutron stars are the incredibly dense leftovers of massive stars that exploded as supernovae. When two neutron stars spiral toward each other and collide, an incredible amount of energy is released, along with huge amounts of neutron-rich material. This environment is perfect for the R process, meaning that neutron star collisions are a major source of some of the rarest and heaviest elements in the universe, including gold, platinum, and rare earth metals. In fact, it's believed that the gold in your jewelry and the uranium in nuclear power plants may have originated from one of these cosmic crashes billions of years ago. Not all elements are made inside stars or explosions. Some are created through an entirely different process called cosmic ray spallation. Cosmic rays are high-energy particles constantly zipping through space at nearly the speed of light. When they slam into atoms floating in space, they shatter them into smaller pieces, creating new, lighter elements in the process. This is how rare elements like beryllium, B, and boron, B, are formed. Cosmic ray spallation happens not only in deep space but also in our own solar system, on asteroids, meteoroids, and even in Earth's atmosphere. Some of the rare isotopes found on Earth, called cosmogenic nuclides, come from this process. While most of the universe's elements were forged in the stars, Earth itself still produces new atomic nuclei through radioactive decay. This is a slow process in which unstable atoms, called radioisotopes, gradually break down into lighter elements over time. For example, uranium, thorium, and potassium-40, which have existed since Earth's formation, continue to decay, releasing radiation and transforming into different elements. This process is responsible for some of the heat inside our planet, driving volcanic activity and plate tectonics. Every element in your body, every metal in your phone, every drop of water in the ocean came from the universe's nuclear factories. The Big Bang, the hearts of stars, exploding supernovae, neutron star collisions, and cosmic rays. The universe is essentially a vast recycling system, continuously forming, destroying, and reshaping elements over billions of years. Even today, new stars are forming from the remnants of older ones, continuing the cycle of element creation. And perhaps billions of years in the future, atoms from our sun will one day be part of new planets, new life forms, or even another intelligent civilization gazing at the stars, wondering where it all began. Only a few minutes after the Big Bang, the universe had cooled enough for these protons and neutrons to start sticking together, forming the very first atomic nuclei. This process, known as Big Bang nucleosynthesis, created some of the lightest elements: hydrogen, helium, lithium, and beryllium. These were the only elements formed in significant amounts during this early stage because the conditions were not right for making heavier elements like carbon or oxygen. One key reason for this limitation was time. The universe was expanding rapidly, causing temperatures and densities to drop. The process of fusion, where atomic nuclei combine to form heavier elements, needs both high temperatures and high pressure to continue. But as the universe expanded, it quickly cooled down too much for further element formation, shutting off nuclear reactions after about 20 minutes. While the Big Bang provided the universe with its first batch of elements, it was stars that became the factories for making heavier elements. The first stars formed around 500 million years after the Big Bang, using the hydrogen and helium left over from the universe's birth as their fuel. Inside these stars, under immense heat and pressure, nuclear fusion took place. This process fused hydrogen atoms into helium, and later, as the stars aged, fused helium into even heavier elements like carbon, oxygen, and nitrogen. This is where carbon, the element necessary for life, finally came into existence, something that couldn't happen during the Big Bang itself. However, not all stars were capable of producing elements heavier than carbon. It took the violent deaths of massive stars, supernova, to create elements like iron, gold, and uranium. When a star exploded in a supernova, it released an enormous burst of energy, allowing for the rapid fusion of elements heavier than iron. Interestingly, some of the light elements like lithium, beryllium, and boron were not just formed in the Big Bang, but also created later by cosmic rays. Cosmic rays are high-energy particles, mostly protons, that travel through space at nearly the speed of light. When they collide with atoms in interstellar gas and dust, they break apart heavier elements into smaller fragments, a process known as cosmic ray spallation. This means that even billions of years after the Big Bang, these lighter elements continued to form in space. The formation of elements beyond iron required even more extreme conditions than those found in normal stars. Some of these heavier elements, including gold, platinum, and uranium, were created in the mergers of neutron stars, ultra-dense remnants of massive stars. When two neutron stars collide, they create intense bursts of energy, triggering nuclear reactions that produce some of the rarest elements in the universe. Additionally, on Earth, some elements like argon-40 were produced through radioactive decay, a natural process where unstable atoms break down over time, changing into different elements. Over billions of years, Earth's composition has been shaped by a mix of nuclear reactions in space, cosmic rays, and geological processes. The study of how elements form, known as nuclear astrophysics, continues to be a major field of research. Scientists analyze stars, supernovae, and neutron star mergers to better understand how different elements were created. Even though the Big Bang marked the beginning of element formation, the story of nucleosynthesis has been ongoing for billions of years, shaping everything we see around us today, from the air we breathe to the gold in our jewelry and the carbon in our bodies. The elements that make up everything in the universe, from distant galaxies to our very own DNA, originated in the fiery birth of the cosmos, evolved inside ancient stars, and were scattered across space by cosmic explosions and high-energy particles. The universe is, quite literally, a giant cosmic laboratory where nature has been crafting the ingredients of life for billions of years. At the beginning of human scientific thought, the origin of chemical elements was a complete mystery. Early ideas suggested that all the elements were created at the very start of the universe. However, scientists could not figure out a rational way for this to happen. As research continued, it became clear that the most common elements in the universe were hydrogen and helium. Together, they made up nearly all the known matter in the cosmos, while all other elements, like oxygen, carbon, and iron, made up less than 2% of the total mass of the solar system and other star systems. At the same time, scientists observed something interesting. Oxygen and carbon were the next most common elements after hydrogen and helium. They also noticed a pattern. Lighter elements, especially those made up of whole numbers of helium-4 nuclei, also called alpha particles, were more abundant than others. But where did all these elements come from? In 1920, British astrophysicist Arthur Stanley Eddington had a bold idea. He suggested that stars generate their immense energy by fusing hydrogen atoms together to form helium. Not only that, but he also proposed that stars could be responsible for creating heavier elements. However, at the time, scientists did not yet understand how nuclear fusion worked, so Eddington's idea was not widely accepted. Still, his idea laid the foundation for future discoveries. Just before World War II, German-American physicist Hans Bethe finally worked out the exact nuclear reactions that power stars. He explained how hydrogen atoms fuse together under extreme heat and pressure inside stars to form helium, a process that releases an enormous amount of energy. This process, known as nuclear fusion, is what keeps stars shining for billions of years. After World War II, Fred Hoyle, a British scientist, expanded on Bethe's work. He tackled an even bigger question: how do stars create heavier elements like carbon, oxygen, and iron? Hoyle's research led him to a groundbreaking discovery. He proposed that all the elements in the universe, beyond hydrogen and helium, were created inside stars. As stars aged and went through different stages of their life cycles, they acted like giant cosmic furnaces, fusing lighter elements into heavier ones. When these stars eventually exploded in supernovae, they scattered the newly formed elements into space, enriching the universe with the building blocks needed for planets and life. But Hoyle had another radical idea. He suggested that hydrogen itself was continuously being created from the vacuum of space. He believed that the universe did not have a singular beginning, but was instead in a constant state of creation. This idea was part of what he called the steady-state theory, which opposed the idea of a single creation event, such as the Big Bang theory. The idea that the universe had a beginning had actually been proposed much earlier. In 1931, Georges Lemaitre, a Belgian physicist and priest, suggested that the universe started from a single, incredibly dense point he called the primeval atom. Over time, this point expanded, giving birth to all the matter and space we see today. Interestingly, it was Hoyle himself who coined the term Big Bang in a 1949 BBC radio broadcast. He used the phrase to describe Lemaitre's idea in contrast to his own steady-state theory. Many believe Hoyle meant it as an insult, but he later clarified that he was simply trying to make the concept easier to visualize. While Hoyle strongly opposed the Big Bang theory, it turned out that both ideas were needed to explain how elements formed. The Big Bang theory helped explain why there was so much hydrogen and helium in the universe, as well as why some light elements like deuterium and lithium were present. On the other hand, Hoyle's work on stellar nucleosynthesis explained how heavier elements formed inside stars. In the 1950s and 1960s, Hoyle's ideas were expanded upon by other scientists, including William A. Fowler, Alistair G.W. Cameron, and Donald D. Clayton. Their work built a clearer picture of how stars evolve and produce different elements. One of the most important papers in this field was published in 1957 by E. Margaret Burbidge, Jeffrey R. Burbidge, William A. Fowler, and Fred Hoyle. This paper, often referred to simply as the B2FH paper, after the author's initials, became a cornerstone of modern astrophysics. It outlined the different nuclear processes that occur inside stars, transforming one element into another. At the same time, scientists were also studying the natural abundances of elements in meteorites. Hans Suess and Harold Urey created an abundance table, which showed how the different elements were distributed in the universe. When they plotted the amounts of each element on a graph, they found that the pattern looked like a jagged sawtooth shape, meaning some elements were much more common than others. This unusual pattern provided important clues about how elements formed in different environments, from the fiery cores of stars to the violent explosions of supernovae. Today, scientists understand that different types of stars create different elements depending on their size and stage of life. Small stars, like the Sun. These stars mainly fuse hydrogen into helium over billions of years. When they run out of hydrogen, they swell into red giants and begin fusing helium into carbon and oxygen. Massive stars. These stars burn through their fuel much faster. As they age, they go through a series of fusion reactions, creating heavier and heavier elements. They can produce neon, magnesium, silicon, and even iron. Supernovae. When a massive star reaches the end of its life, it explodes in a supernova. This explosion is so powerful that it creates even heavier elements, such as gold, silver, and uranium. These elements are then scattered into space, eventually becoming part of new stars, planets, and even living beings. Neutron star collisions. Recent discoveries have shown that when two neutron stars collide, they produce a tremendous amount of rare, heavy elements like gold and platinum. This process, known as the R process, helps explain the presence of these elements on Earth. Understanding nucleosynthesis is not just about knowing where elements come from. It helps us understand the history of the universe itself. The elements that make up our bodies, our planet, and everything we see were forged in the hearts of ancient stars billions of years ago. Every atom of oxygen in the air we breathe, every carbon atom in our bodies, and every drop of water we drink has a cosmic origin. The study of nucleosynthesis continues to evolve, with new discoveries shedding light on the processes that shape the universe. By studying distant stars, supernovae, and neutron star collisions, scientists are constantly uncovering new insights about how the elements formed and how the universe continues to change. In the grand scheme of things, we are all made of stardust, pieces of ancient stars that lived and died long before our solar system was born. And that, perhaps, is the most fascinating story of all. The process of nucleosynthesis, the creation of elements in space, is a fascinating and essential part of the universe's life cycle. It is responsible for the formation of elements from hydrogen and helium to some of the heaviest elements we find in the periodic table today. These processes primarily occur in stars, which act as the cosmic factories where elements are forged. The way stars create these elements is an incredible chain of nuclear reactions, known as the process of stellar nucleosynthesis. Understanding this process gives us a glimpse into the heart of stars and how the elements that make up everything around us came to be. At the heart of every star is nuclear fusion, a process that powers the star and produces the elements found in the universe. These nuclear reactions start with hydrogen atoms, which are the simplest and most abundant element in the universe. In stars, hydrogen atoms fuse together to form helium through a series of reactions. This process is called hydrogen burning. There are two primary ways this happens: the proton-proton chain and the CNO cycle. In the proton-proton chain, hydrogen atoms, protons, collide and fuse to form helium-4, releasing energy in the form of light and heat. This is the dominant process in smaller stars like our Sun. The CNO cycle, on the other hand, is more important in heavier stars. It also fuses hydrogen into helium, but uses carbon, nitrogen, and oxygen as catalysts to drive the reaction. After hydrogen has been used up in a star's core, the star begins to burn helium. This phase is known as helium burning, where helium atoms fuse together to create heavier elements, such as carbon and oxygen. As the star ages and the temperature and pressure in its core rise, it can begin to burn heavier elements. The sequence of burning heavier and heavier elements continues in a chain reaction that includes carbon burning, neon burning, oxygen burning, and silicon burning. These steps create elements up to and including iron and nickel. Iron is special in the world of nucleosynthesis because it has the highest binding energy per nucleon. This means that no matter how much energy is put into fusing iron atoms, the process will not release energy. In fact, trying to fuse iron requires energy instead of releasing it. This is why iron marks the end of the process of energy-producing fusion in stars. But what about the elements heavier than iron, like gold, uranium, and platinum? These elements cannot be formed in the same way as the lighter ones. Instead, they are created through a process called neutron capture. In stars, especially in extreme environments, atoms can capture neutrons, leading to the formation of heavier elements. This process happens in two main ways: the S process and the R process. The S process, or slow neutron capture process, occurs in stars during their later stages. It involves the capture of neutrons by atomic nuclei at a relatively slow rate. As neutrons are captured, the atomic nuclei become heavier and heavier. These new, heavier elements are eventually released into space when the star dies and explodes in a supernova or sheds its outer layers in a planetary nebula. These elements then mix into the interstellar medium, enriching the universe with heavier elements that will later form new stars, planets, and even life. The R process, or rapid neutron capture process, happens in more extreme environments, such as during supernova explosions or neutron star mergers. In these violent events, the rate of neutron capture is so high that elements heavier than iron can form in just a few seconds. The R process is responsible for the creation of many of the heaviest elements in the universe, including gold and uranium. Supernovae, the powerful explosions of massive stars at the end of their lives, are one of the key environments for nucleosynthesis. During a supernova, a star releases an enormous amount of energy and matter into space. This explosion is so powerful that it creates elements much heavier than iron. When a massive star reaches the end of its life, it can no longer fuse elements in its core. The star collapses, and the explosion produces a shockwave that causes the outer layers of the star to blow off, forming a supernova. During this explosion, the extreme conditions allow for the formation of heavy elements like gold, platinum, and uranium through the R process. In addition to supernovae, neutron star mergers are also believed to be a significant source of heavy elements. When two neutron stars, the remnants of supernovae, collide, they create a burst of energy and release large amounts of heavy elements into space. This event is also believed to produce elements like gold and platinum, adding to the cosmic collection of heavy elements that make up the universe. Before stars existed, there was the Big Bang. In the early moments of the universe, temperatures and pressures were so high that nuclear fusion could occur freely. This period, known as Big Bang nucleosynthesis, took place within the first 3 minutes of the universe's existence. During this time, the universe was still very hot and dense, filled with a glowing mixture of quarks, electrons, and other particles. As the universe began to cool, protons and neutrons formed, and nuclear reactions started to take place. During Big Bang nucleosynthesis, a number of light elements were created. These included hydrogen, the most abundant element in the universe, helium, the second most abundant, and small amounts of lithium and beryllium. The process was incredibly short-lived, lasting only about 20 minutes, after which the universe had expanded and cooled too much for nucleosynthesis to continue. By the end of this period, most of the matter in the universe was in the form of hydrogen and helium, with trace amounts of heavier elements like lithium and beryllium. One of the key things we learn from Big Bang nucleosynthesis is that the light elements created in this process make up a large portion of the mass of the universe. For example, almost all of the helium in the universe was formed during the Big Bang, and it continues to be produced in stars today. The processes of nucleosynthesis, whether they occur in the early universe, in the hearts of stars, or in the aftermath of supernovae and neutron star mergers, have shaped the universe and everything in it. They are responsible for creating the elements that make up stars, planets, and even life itself. Without nucleosynthesis, the elements we know today, like carbon, oxygen, and iron, would not exist. By studying nucleosynthesis, astronomers and physicists can learn more about the history and evolution of the universe. The patterns of elements found in different stars and galaxies can reveal information about how those stars formed and the types of processes that occurred in their cores. It also helps us understand the origins of the elements that are essential for life, such as carbon and oxygen, and how those elements have been recycled and distributed across the cosmos. Stellar nucleosynthesis is the process in which stars create new elements. It happens inside stars as they go through their life stages, and it's responsible for producing elements like carbon, oxygen, and iron. Stars act like gigantic furnaces, where lighter elements like hydrogen and helium are fused into heavier elements. As stars age and their cores get hotter, this fusion process becomes more complex, creating more and more heavy elements. One of the most important elements created in this process is carbon. This is because carbon forms through a special process called the triple alpha process, and it's a key step that allows further creation of even heavier elements. Carbon also plays a vital role in releasing free neutrons inside stars. These neutrons then contribute to the S process, where iron atoms absorb neutrons and transform into even heavier elements like gold and uranium. After the stars make these new elements, they don't keep them to themselves. The elements are released into space when the stars lose mass, either through gentle winds from low-mass stars or during massive explosions in the case of supernovae. These explosions, especially from stars that are much larger than our Sun, spread the newly created elements into space, enriching the gas and dust that eventually form new stars and planets. The first solid proof that stars are responsible for creating heavy elements came when scientists noticed that the gas between stars, known as interstellar gas, became gradually richer in these elements over time. Stars that formed later in the galaxy were born with more heavy elements than older stars. In 1952, scientists discovered technetium, a radioactive element, in the atmosphere of a red giant star. This was groundbreaking because technetium has a very short lifespan, meaning it had to have been created recently in that star. This discovery was one of the first signs that nuclear reactions were happening inside stars. More evidence came from the observation of certain elements like barium in stars. Stars on the asymptotic giant branch, a late phase in their life, showed barium levels much higher than what was found in younger stars. This confirmed that the S process was at work inside those stars, creating heavier elements. One of the most exciting pieces of evidence for stellar nucleosynthesis comes from something called stardust, or presolar grains. These tiny solid particles which formed from the gases around stars are often found in meteorites. By studying their isotopic makeup, scientists can learn a lot about the chemical processes that happened inside stars before they died. These grains offer a direct window into the life cycle of stars, providing valuable clues about how stars create the elements we find in the universe today. Supernovae, those incredibly powerful stellar explosions, are more than just dramatic cosmic events. They are among the universe's primary factories for creating heavy elements, ones that play a fundamental role in the composition of matter in the universe. The process by which elements are made during a supernova is called supernova nucleosynthesis. It's a process that occurs in the intense environment of a supernova, where temperatures and pressures are so high that nuclear reactions take place at an incredibly fast rate. Through these reactions, elements between silicon and nickel are created. In a supernova, when a star explodes, it generates such an energetic environment that nuclear fusion reactions occur at a remarkable pace. These reactions allow atoms to combine and form new, heavier elements. The process primarily produces elements that have atomic numbers between silicon, which has an atomic number of 14, meaning it has 14 protons, and nickel, with an atomic number of 28. These elements are formed through a process called quasi-equilibrium. Quasi-equilibrium can be thought of as a state that is very close to equilibrium. In other words, the nuclear reactions are almost in balance, but not quite. There is a particular imbalance caused by the very high abundance of silicon nuclei in the mix of atoms involved. This imbalance creates a unique set of nuclear conditions that make the formation of elements possible in a supernova's core. The concept of quasi-equilibrium was a significant breakthrough in nucleosynthesis theory. Before this discovery, scientists believed that the formation of these intermediate elements in supernovae was controlled by a different process known as the alpha process, as described in the 1957 B2FH paper, named after the authors Burbidge, Fowler, and Hoyle. This alpha process involved the repeated addition of helium nuclei, alpha particles, to lighter elements to form heavier ones. However, the theory of quasi-equilibrium proved to be much more accurate in explaining how these elements come into existence, replacing the older, less correct alpha process. In addition to the process that forms elements from silicon to nickel, another key mechanism of element creation in supernova is the R process, or rapid neutron capture process. The R process is responsible for creating some of the heaviest elements in the periodic table, elements like uranium and thorium, which are critical to the universe's natural radioactive background. The R process occurs when an atomic nucleus rapidly captures neutrons and subsequently undergoes a series of transformations. What makes the R process unique is that it happens very quickly, so quickly that the captured neutrons do not have time to decay. This rapid process of neutron absorption builds up heavier and heavier nuclei. The free neutrons are created during a supernova's core collapse, particularly by a phenomenon known as electron capture, where electrons are absorbed by protons, turning them into neutrons. This is one of the key processes in creating the free neutrons necessary for the R process. Interestingly, this R process is not dependent on the specific elements present in the star before the explosion. Even if a star is made up mostly of hydrogen, H, and helium, He, which are the two simplest elements, the R process can still occur. This is because the R process is driven by the neutron-rich environment that forms during the collapse of the supernova's core, not the pre-existing composition of the star. Astronomers have gathered strong evidence that the R process is indeed responsible for the creation of many of the heaviest elements. For example, observations of very old stars with low metallicity, meaning they contain fewer heavy elements, show that they still have a full complement of R process elements, demonstrating that these elements were produced through the R process during the early history of the universe, long before the stars we observe today were even formed. The R process is essential not only for creating heavy elements, but also for producing the most neutron-rich isotopes of elements, which are vital to understanding the nature of the universe's elemental makeup. However, despite much progress, scientists have not yet fully understood the details of how the R process works in supernova, and accurate calculations of R process abundances are still a challenge. Another important process in the universe's element creation toolkit is the RP process, or rapid proton capture process. This process involves the rapid absorption of protons in addition to neutrons. While this process is similar to the R process, it differs in its use of protons instead of neutrons to build heavier nuclei. However, unlike the R process, the RP process remains somewhat uncertain in terms of its existence and role in nucleosynthesis. It's theorized to play a part in the formation of lighter elements that are proton-rich, but its exact contribution to supernova nucleosynthesis is still under investigation. Some scientists believe that the RP process could be important in certain types of stars, but more research is needed to confirm this. When a supernova explodes, it does so with a tremendous release of energy. This explosion is so fast that radioactive decay, the process by which unstable nuclei break down over time, doesn't have time to significantly alter the process of element formation. As a result, the supernova nucleosynthesis process can produce elements with equal numbers of protons and neutrons, which are stable and highly abundant. One of the key steps in this process is the fusion of oxygen and silicon nuclei at extremely high temperatures. This fusion forms new, heavier nuclei up to the element nickel. The resulting elements include various forms of titanium, chromium, iron, and nickel. For example, nuclei made up of equal numbers of protons and neutrons, like the 56 Ni isotope, are stable up to certain limits. However, not all nuclei created during this process are stable. Some of them are radioactive and will decay into other elements. For instance, isotopes like 44 Ti, 48 Cr, 52 Fe, and 56 Ni are created in abundance during a supernova explosion, but are radioactive. Over time, they decay into more stable forms, such as 48T, 52Cr, and 56 Fe. One of the fascinating aspects of supernova nucleosynthesis is the production of gamma rays. These are high-energy photons, a form of radiation, emitted during the decay of radioactive isotopes. The gamma rays emitted by these decays are important because they can be detected by instruments in space, allowing scientists to study the processes that take place in a supernova explosion. The detection of these gamma rays was one of the key breakthroughs in the field of gamma-ray astronomy. In 1987, astronomers observed a supernova explosion, known as Supernova 1987A, which provided one of the most significant confirmations of explosive nucleosynthesis. Gamma-ray lines were detected coming from the explosion, specifically identifying isotopes like 56Co and 57Co. These isotopes, formed through the decay of their radioactive cobalt parents, had half-lives that limited their age to about a year. This observation confirmed that these isotopes were produced during the explosion and that the process of explosive nucleosynthesis had indeed taken place. These gamma-ray emissions were not just a random occurrence. They were predicted back in 1969 as a key way to observe and confirm the nucleosynthesis processes occurring inside a supernova. This prediction played a crucial role in the planning of NASA's Compton Gamma Ray Observatory, which was designed to detect such gamma-ray emissions. In addition to the gamma-ray observations, there is another line of evidence for supernova nucleosynthesis found in tiny grains of stardust. These grains are microscopic particles that form in the cooling and expanding remnants of a supernova explosion. As these grains cool, they trap specific isotopic signatures that scientists can study to learn more about the nucleosynthesis processes that took place. One of the most intriguing discoveries is the presence of radioactive 44 Ti in these stardust grains. The high abundance of 44T in supernova stardust confirmed predictions made in the 1970s about the identification of these grains, which are now known as pre-solar grains. These grains offer a snapshot of the chemical processes that occurred in the star before it exploded, providing a window into the early stages of nucleosynthesis in the universe. The merger of binary neutron stars, BNS, has recently been recognized as a key source of some of the heaviest elements in the universe. Neutron stars, which are extremely dense remnants of massive stars, are known to contain an abundance of neutrons. Scientists had long suspected that when two neutron stars collided, they could produce heavy elements. But they couldn't confirm this until a groundbreaking event in 2017. During that year, multiple scientific organizations, including LIGO, Virgo, and the Fermi Gamma Ray Space Telescope, observed both gravitational waves and electromagnetic signals from a possible neutron star merger named GW170817. This discovery marked the first direct evidence of a neutron star collision and revealed a wealth of heavy elements, such as gold, in the debris of the collision. The heavy elements are formed when the degenerate matter that is highly compressed, starts to decay and cool down after the merger. This event helped scientists better understand how heavy elements are produced. While neutron star mergers are now seen as the primary contributors to these elements, another significant discovery occurred in 2021 when the first neutron star black hole merger, NSBH, was detected. However, most research suggests that BNS mergers are more likely to be the main source of these heavy metals. The ongoing study of these cosmic phenomena is helping scientists unlock the mysteries of how the elements that make up our world came into existence. In addition to these mergers, nucleosynthesis, the process of creating new elements, can also happen in the accretion disks of black holes. An accretion disk is a rotating disk of matter that forms around a black hole. As material gets drawn into the black hole's intense gravitational field, it heats up and can produce various elements in the process. Another fascinating process at play in the universe is cosmic ray spallation. This phenomenon occurs when fast-moving cosmic rays, mostly protons, collide with interstellar matter, breaking it apart. This process creates some of the lightest elements, such as lithium, beryllium, and boron, which are essential building blocks in the universe. It is also responsible for creating most of the helium-3 found in space, though some of it may have been formed during the Big Bang. The impact of cosmic rays fragments carbon, nitrogen, and oxygen nuclei, and in doing so, creates these light elements in greater quantities than would be expected in the Sun's atmosphere. However, cosmic ray spallation does not significantly contribute to the production of hydrogen and helium, as these elements already exist in vast amounts from the time of the universe's formation. Beryllium and boron are not typically produced in large quantities through stellar fusion because beryllium-8 decays almost immediately after it is formed. Its half-life is incredibly short. Because of this, these elements are largely created through spallation and other cosmic processes rather than through fusion in stars. To understand these processes, scientists test various theories by calculating the abundances of isotopes, different forms of an element that have the same number of protons but a different number of neutrons. By comparing the calculated abundances with those observed in the universe, researchers can confirm or refine their theories about how elements were made. On Earth, tiny amounts of certain elements called nuclides are produced artificially. For example, we can create technetium in laboratories, but most of the nuclides we find on Earth are the result of natural processes. These nuclides help scientists trace the origins of geological events and date rocks. Although they are found in tiny quantities, these naturally occurring nuclides play an essential role in understanding the Earth's history and the ongoing cycles in nature. One way nuclides are formed is through radioactive decay. When large, unstable atomic nuclei decay, they release smaller particles known as radiogenic daughter nuclides. For instance, the decay of uranium-235 and uranium-238 over millions of years produces a variety of intermediate nuclides, which ultimately decay into stable elements, such as lead. Similarly, the radioactive decay of potassium-40 in the Earth's crust produces argon-40, which is a key component of Earth's atmosphere. Most of the helium found in the Earth's crust is also a result of alpha decay, where a nucleus releases a helium atom. In addition to radioactive decay, another process called spontaneous fission occurs. During fission, the nucleus of a heavy atom splits into two smaller fragments, releasing energy and creating new nuclides. Thorium-232, uranium-235, and uranium-238 all undergo spontaneous fission, and it's through this process that elements like technetium and promethium are produced. Nuclear reactions, particularly those that happen during radioactive decay, also contribute to the creation of new elements. These processes are referred to as nucleogenic, and they occur when energetic particles, often from radioactive decay, collide with other nuclei, causing them to transform into different elements. Neutrons, which are produced during spontaneous fission, can also participate in these reactions, causing further changes in the nuclei they collide with. These processes play a crucial role in the creation of many elements found on Earth, such as neon-21 and neon-22. Cosmic rays also contribute to the production of new elements, which is known as cosmogenic nucleosynthesis. For example, when cosmic rays strike nitrogen-14 in the atmosphere, they transform it into carbon-14, an isotope used in dating ancient objects. Other examples include iodine, 129 and other isotopes that continue to form as cosmic rays interact with Earth's atmosphere. These various natural processes not only help us understand how elements are created across the universe, but also shed light on the fundamental workings of our planet. The production of elements through cosmic and nuclear processes continues to be a fascinating area of study, one that reveals the interconnectedness of the cosmos, the Earth, and all that exists within them. Cosmic inflation is one of the most important concepts in modern cosmology, as it helps explain the creation of the universe and the patterns we see in it today. In simple terms, cosmic inflation is the theory that, in the very early moments after the Big Bang, the universe expanded at an incredibly fast rate, much faster than anything we could ever imagine. This period of rapid expansion played a crucial role in shaping the universe, determining its structure, and setting the stage for everything that came after. But cosmic inflation didn't just happen on its own. It was the result of a delicate balance of forces, each playing its part in creating the universe we now observe. These forces, such as gravity, quantum mechanics, and the energy fields that existed in the early universe, work together in complex ways, setting the foundation for galaxies, stars, planets, and even life itself. Before we talk about cosmic inflation, it's important to understand the Big Bang. The Big Bang wasn't an explosion in the traditional sense, but rather an event in which the universe began to expand from an extremely hot, dense, and tiny point. Everything in the universe was concentrated into this tiny space, and as it started to expand, the universe began its journey toward becoming the vast and complex entity we know today. However, there's a problem with the Big Bang theory when it's taken on its own. It doesn't explain why the universe is so uniform. If you look out into space, the universe appears to be mostly the same in all directions, with galaxies and stars scattered in a pattern. But how did that uniformity come to be, especially considering that the universe started out so chaotic and unstable? Cosmic inflation is a theory that was proposed in the early 1980s by physicist Alan Guth. It suggests that during the first few moments of the universe's existence, it underwent a period of extremely rapid expansion. This expansion happened much faster than the speed of light. To put it in perspective, imagine something the size of a tiny grain of sand suddenly stretching to the size of the entire observable universe in just a fraction of a second. That's how fast the universe expanded during this time. The idea behind cosmic inflation is that the universe began as a small, hot, and incredibly dense point, but in just a tiny fraction of a second. The universe expanded by a huge amount. This rapid inflation helped smooth out any irregularities and created the uniformity we see in the cosmos today. It also explains why distant galaxies are so far apart from each other and why the universe looks the same in all directions. Now let's talk about the forces that played a role in cosmic inflation. Several fundamental forces of nature work together to make this rapid expansion happen. These forces include gravity, quantum mechanics, and the energy field known as the inflaton field. Gravity, the force that pulls objects toward each other, is one of the most familiar forces we encounter every day. It keeps us anchored to the ground and causes objects to fall toward the Earth. But gravity also has a more powerful role in the universe, especially during the early stages of the cosmos. In the context of cosmic inflation, gravity played a role in shaping the way the universe expanded. During inflation, the gravitational force was weak compared to the energy produced by the inflaton field. However, after inflation ended, gravity became the dominant force in the universe, causing matter to clump together and form stars and galaxies. Quantum mechanics is the branch of physics that deals with the smallest particles in the universe, things like atoms, electrons, and photons. Unlike the predictable behavior of objects we see every day, particles at the quantum level behave in strange and unpredictable ways. These particles exist in a state of probability, meaning they can be in many different places or states at once. During cosmic inflation, quantum mechanics played a significant role in the fluctuations that helped create the large-scale structure of the universe. Tiny quantum fluctuations in the inflaton field caused small variations in the density of the universe. These fluctuations grew over time, eventually leading to the formation of galaxies, clusters of galaxies, and other structures we see in space. The inflaton field is a hypothetical field that is thought to have existed during the early universe. This field is believed to have driven the rapid expansion of the universe during the inflationary period. In simple terms, the inflaton field acted like a form of energy that caused space to expand exponentially. As the field interacted with the universe's other forces, it provided the necessary energy to fuel cosmic inflation. When the inflaton field lost its energy, the universe slowed down and began to expand at a much slower rate. This transition from rapid inflation to the more gradual expansion we see today is known as reheating, and it marked the beginning of the universe's current structure. After the inflationary period ended, the universe was no longer expanding at such an extreme rate. However, the effects of inflation were still very much present. The fluctuations caused by the quantum field led to tiny differences in the density of matter and energy, which eventually became the seeds for the formation of galaxies, stars, and other cosmic structures. These density fluctuations caused matter to clump together under the influence of gravity. Over billions of years, this process resulted in the formation of stars, galaxies, and even larger structures like galaxy clusters. The distribution of matter in the universe today is largely a result of the patterns created by these fluctuations during the inflationary period. One of the most fascinating aspects of cosmic inflation is how different forces work together to create the universe as we know it. It wasn't just a single force that caused the universe to expand rapidly. Instead, it was a combination of forces, gravity, quantum mechanics, and the inflaton field, that created the right conditions for inflation to happen. This delicate balance of forces is a key part of why the universe has the structure and properties it does. For example, if the force driving inflation had been too weak, the universe wouldn't have expanded fast enough to smooth out the irregularities we see today. On the other hand, if inflation had been too strong, the universe could have expanded too quickly, preventing the formation of galaxies and stars. The forces that caused inflation also laid the groundwork for the formation of the universe's large-scale structure. By creating density fluctuations in the early universe, inflation provided the seeds for the cosmic web, the vast network of galaxies and galaxy clusters that stretch across the universe. These fluctuations grew over time, giving rise to the galaxies and stars we see today. Cosmic inflation has profound implications for how we understand the universe. It suggests that the universe wasn't created from a singular event, but rather from a highly complex and finely tuned process that involved multiple forces working together. The universe's current structure, including the distribution of galaxies and the cosmic background radiation, can all be traced back to this period of rapid expansion. In the field of astronomy, dark matter is a strange and invisible kind of matter that we can't see because it doesn't interact with light or any other type of radiation. We know it exists because of the odd effects it has on gravity, which can't be fully explained by the laws of physics unless there's more matter around than we can actually see. These strange effects show up when we study things like how galaxies form and change over time, how light bends around huge objects, called gravitational lensing, and even the way galaxies move within groups. We also notice its influence in the structure of the universe and the leftover radiation from the Big Bang, the cosmic microwave background. In the most widely accepted model of the universe, known as the lambda CDM model, the universe's total mass and energy is made up of 5% regular matter, the kind we see around us, 26.8% dark matter, and 68.2% dark energy. That means dark matter makes up about 85% of the total mass, while dark matter and dark energy together make up 95% of the universe's total energy. We don't know exactly what dark matter is, but it doesn't seem to interact with regular matter or light, except through gravity, making it nearly impossible to detect with our current technology. The main theory is that dark matter might be made up of tiny unknown particles, such as weakly interacting massive particles, WIMPs, or axions. Another possibility is that dark matter could be made of ancient black holes from the early universe. Dark matter can be grouped in different ways based on how fast its particles move, cold, warm, or hot. Most scientists think dark matter is cold, meaning its particles move slowly, allowing them to gather together and form structures over time. While most astrophysicists believe dark matter exists, some still question the idea. A small group of scientists, confused by certain observations that regular dark matter doesn't fully explain, suggest that maybe the laws of gravity need to be changed. They've proposed alternative theories like modified Newtonian dynamics or new types of gravity, but none of these theories can perfectly explain all the evidence we've gathered so far. This suggests that, even if gravity needs some changes, dark matter still seems to be an important part of the puzzle. The idea of dark matter has a long and fascinating history, filled with interesting discoveries and theories that laid the foundation for our current understanding of the universe. The story begins with the work of some of the brightest minds in science, starting in the late 19th century. In 1884, William Thomson, better known as Lord Kelvin, made some interesting observations. He talked about the possible number of stars around our sun in a book based on a lecture series he gave in Baltimore. Kelvin was trying to estimate the number of stars near the sun. He did this by studying how stars moved around our solar system. Using this information, he wondered what would happen if there were 1 billion stars within a distance of 1 kiloparsec from the sun. At this distance, the stars would appear to move in ways that were hard to explain, and this idea led to further thinking about invisible matter in space. Lord Kelvin also estimated the sun's age to be between 20 and 100 million years, which was later shown to be wrong. But his curiosity about the stars and their movement helped start early thoughts on dark matter. A couple of decades later, in 1906, the French mathematician and physicist Henri Poincaré introduced the term dark matter or matière obscure while talking about Lord Kelvin's work. Poincaré suggested that there might be hidden mass in the universe, but he also thought that this hidden matter would be less than the visible matter we can see. Although his ideas were far from correct, Poincaré's mention of dark matter brought the idea into the scientific conversation. In the 1920s, dark matter continued to interest astronomers. In 1922, Dutch astronomer Jacobus Kapteyn became one of the first to use the speeds of stars to suggest the existence of dark matter. He noticed that the way stars moved in space could be affected by unseen forces, hinting at the presence of invisible matter. Then, in 1930, Swedish astronomer Knut Lundmark further expanded on the idea, realizing that the universe must have much more mass than we could observe with our telescopes. This discovery was important because it showed that the visible universe might not be the complete picture. In 1932, another Dutch scientist, Jan Oort, joined the discussion by suggesting that dark matter might exist in the galactic neighborhood. Oort studied the movements of stars near our galaxy and concluded that there must be more mass in our galaxy than was visible. However, he later realized that his measurements weren't completely accurate, and more research would be needed to understand the true nature of this unseen mass. Then, in 1933, Swiss astrophysicist Fritz Zwicky made a big breakthrough while studying galaxy clusters at the California Institute of Technology. Zwicky was studying the Coma cluster, a large group of galaxies, and noticed something strange. The galaxies in the cluster were moving much faster than expected based on the visible mass. This led him to suggest the presence of a huge amount of invisible mass, which he called dunkle materie, dark matter. Zwicky estimated that the Coma cluster had around 400 times more mass than could be seen through telescopes based on how the galaxies were moving. He believed that this unseen mass was responsible for the gravitational force that kept the galaxies in the cluster together. Although Zwicky's estimates were wrong by a large amount, mainly due to outdated values, he was one of the first to correctly identify that the universe must contain unseen mass that pulls things with gravity. Zwicky, however, had a different view of dark matter than we have today. He believed that dark matter was simply ordinary matter that didn't give off light, rather than something completely different, like the mysterious dark matter we think of today. Still, his work was a major step toward discovering dark matter. As time passed, more proof of the existence of dark matter started to show up. One important piece of this proof came from studying how galaxies spin. In 1939, H.W. Babcock studied the spin of the Andromeda Galaxy, the closest spiral galaxy to us. He found that the stars on the outer edges of the galaxy were moving much faster than expected. This suggested that there was much more mass in the galaxy than could be seen by just looking at its visible stars. At first, Babcock thought that the strange spinning could be due to light being absorbed inside the galaxy, or that the way the galaxy worked was different in its outer parts. But his observations were an early clue that something invisible was affecting the galaxy's spin. The next year, in 1940, Jan Oort made another important discovery. He studied a galaxy called NGC 3115 and found a large invisible halo of mass surrounding it. This was another sign that galaxies might contain hidden matter beyond what we could see with our current technology. The idea of dark matter really began to catch on in the 1970s. Different scientific discoveries came together to suggest that galaxies might be surrounded by huge, invisible halos of matter. In 1974, two separate research groups, one from Princeton, New Jersey, led by Jeremiah Ostreicher, Jim Peebles, and Amos Yahill, and another from Tartu, Estonia, led by Jan Einasto, N. Saar, and Ants Kasik, came to the same conclusion independently, making the idea stronger. One important observation that pointed to the existence of these invisible galactic halos was the way galaxies spin. Both optical and radio astronomy played a major role in these findings. Vera Rubin and Kent Ford, using a new spectrograph, made more accurate measurements of the speed of edge-on spiral galaxies, revealing surprising results in the spinning curves. At the same time, radio astronomers used advanced radio telescopes to study the 21 centimeters line of atomic hydrogen in nearby galaxies. Unlike starlight, which can only be seen from the central parts of galaxies, hydrogen gas extends much farther out. This allowed astronomers to observe spinning patterns at much greater distances, giving them a better picture of the total mass in a galaxy. Early studies of the Andromeda Galaxy, using large telescopes like the 300-foot Green Bank telescope and the 250-foot Jodrell Bank dish, showed that the hydrogen spinning curve didn't behave as expected based on Kepler's laws, which describe how objects should move around a center of gravity. As technology improved, more sensitive equipment allowed for even further measurements. In 1975, Roberts and Whitehurst pushed the limits, measuring the spinning speed of Andromeda all the way out to 30 kiloparsecs. Their findings showed that the galaxy's spinning curve stayed flat even at great distances. This was important because it suggested there was much more mass out there, beyond what we could see with regular telescopes. These findings, shown in their charts, combined optical data with the new hydrogen data, clearly showing the surprising flatness of the outer galaxy spinning curve. The solid curve in the graph represented the optical data from stars, while the other curve showed the total mass, which still kept increasing even in the galaxy's outermost regions. At the same time, scientists were developing even more advanced methods to study galaxies. Using interferometric arrays, multiple radio telescopes working together, researchers like Rogstad and Shostak in 1972 mapped the hydrogen spinning curves of 5 spiral galaxies. They found that all of these galaxies had flat spinning curves as well, suggesting that the mass in the outer parts of the galaxies was much higher than what could be explained by visible stars and light. By the late 1970s, it was widely accepted that dark matter halos likely existed around galaxies, and this became one of the biggest mysteries in astronomy. In the 1980s and 1990s, many observations started to suggest that dark matter was real. One important study, done by Persic, Salucci, and Stell in 1996, looked closely at 967 spiral galaxies and found strong proof of dark matter's existence. Other supporting evidence included strange behaviors like gravitational lensing, where galaxy groups bend light from objects behind them, the spread of hot gas in galaxies and groups, and the way tiny temperature differences, called anisotropies, appear in the cosmic microwave background, which is the afterglow of the Big Bang. Today, most scientists agree that dark matter is made up of particles that we haven't discovered yet, and these particles are unlike anything we know. The search to find this mysterious particle has become one of the biggest quests in particle physics, with many researchers using different methods and experiments to try and uncover the truth. In simple terms, when scientists talk about matter in the universe, they are referring to anything that adds to the overall energy and its density changes in a particular way as the universe expands. Specifically, it decreases as the cube of the expansion, meaning the further the universe stretches, the thinner the matter becomes. This is different from radiation, which decreases even faster. Its energy gets weaker as the universe grows, following the inverse fourth power of the expansion. On the other hand, the cosmological constant behaves differently. It stays the same no matter how much the universe stretches, meaning its energy density remains constant. This difference in how matter, radiation, and the cosmological constant behave is due to a phenomenon called radiation redshift. To picture this, imagine the universe expanding. If the observable universe's size doubles, the scale factor of expansion also doubles. As a result, the energy of things like the cosmic microwave background radiation, the afterglow from the Big Bang, gets weaker because each photon, light particle, has to stretch out over a larger area, reducing its energy. The same happens to ultra-relativistic particles, such as early neutrinos. These lose energy in a similar way. However, the cosmological constant, being a property of space itself, doesn't change no matter how much the universe grows. As for dark matter, this term generally refers to parts of the universe that we cannot see, yet still have mass and obey similar laws to regular matter. However, in more specific terms, dark matter is often used to describe a particular kind of invisible matter that isn't made up of the usual particles we're familiar with, excluding something called missing baryons. Depending on the context, the meaning of dark matter can vary. The arms of spiral galaxies spin around their center, and as you move outward from the center, the visible mass density of the galaxy gets lower. If all the galaxy's mass were visible, it would behave like a simple system where most of the mass is concentrated at the center and objects orbiting it, much like how planets orbit the sun in our solar system. Based on Kepler's third law, we would expect the speeds of the objects to slow down the farther they are from the center, just like how the planets in our solar system move slower the further they are from the sun. But that's not what we see in galaxies. Instead, the rotation speeds of stars and gas in a galaxy remain constant, or even speed up the farther out they are from the center. To explain this strange observation, it seems clear that the spread of mass in spiral galaxies is different from the solar system. Specifically, there may be a large amount of invisible, non-luminous matter, what we call dark matter, on the edges of the galaxy. In bound systems like galaxies, the stars are also governed by a rule called the virial theorem, which helps explain how mass is spread out in a system based on the speeds of the stars. When astronomers look at how fast stars are moving in systems like elliptical galaxies or dense star clusters, they can use this theorem to figure out how mass is spread out. However, in many cases, the measured speeds don't match what we'd expect based on the amount of visible mass in the system, even when we consider complex orbital patterns of the stars. Much like with the rotation curves of galaxies, the most logical explanation for this mismatch is that there's more invisible matter involved. Again, dark matter. Galaxy clusters are key to studying dark matter because we can measure their mass in 3 different ways: by looking at the range of speeds at which the galaxies in the cluster move, by studying the X-rays emitted by the hot gas inside the cluster. By analyzing these X-rays, we can determine the temperature and density of the gas, which lets us calculate the pressure. Using the balance between gravity and pressure, we can figure out the total mass of the cluster. Through gravitational lensing, where the mass of the group bends light from farther objects. This lets us measure the group's mass without needing to directly observe the movement of the galaxies. All 3 of these methods point to the same conclusion. dark matter makes up roughly 5 times the mass of all the visible matter in these groups. One interesting result of Einstein's theory of general relativity is a phenomenon called gravitational lensing. This happens when big objects like galaxies or groups of galaxies sit between a light source and the observer. These big objects act like a lens, bending the light that passes through them, making the light from the source appear distorted. The important thing to know is that gravitational lensing only requires the presence of mass. It doesn't matter what the mass is made of. The more massive an object is, the stronger the bending of light will be. For example, imagine a group of galaxies lying between a very far-away object like a quasar and us. In this case, the galaxies in the group will bend the light from the quasar, making it look different. When we talk about strong lensing, we're referring to the dramatic way the light from background galaxies can be bent into arc shapes as it passes through a big object's gravitational field. This has been observed around many faraway galaxy groups, including one known as Abell 1689. By studying the shape of these arcs, scientists can figure out the mass of the galaxy group causing the bending. In the weak lensing scenario, the bending is much less noticeable, and galaxies don't turn into arcs. Instead, we see tiny distortions in the shapes of galaxies. By looking at these slight changes, scientists can learn about how dark matter is spread out in the universe. The patterns of mass and light from these observations match what we expect from studies of dark matter. Now, while both dark matter and regular matter are forms of matter, they behave very differently. Early in the universe, regular matter was charged and interacted strongly with light, which caused it to scatter. Dark matter, on the other hand, doesn't interact directly with light, but it still affects the universe in other ways. For example, it influences the cosmic microwave background, CMB, through its gravitational pull, especially on large scales. It also has an effect on the movement and density of regular matter. Because of these differences, regular matter and dark matter evolve in separate ways and leave distinct traces on the CMB. The CMB is very close to being a perfect blackbody, meaning it gives off a smooth, even temperature. However, there are tiny temperature differences, about 1 part in 100,000, that scientists can study. These small variations, called anisotropies, can be mapped out across the sky. When scientists break down this map into a graph called the angular power spectrum, they see a series of peaks that are evenly spaced but have different heights. The exact positions of these peaks depend on key factors in cosmology, and by comparing these positions to theoretical models, we can learn more about the universe's makeup. The first discovery of the CMB's anisotropies came in 1992 by the COBE satellite, but the resolution wasn't high enough to see the detailed peaks. In 2000, the Boomerang experiment, using a balloon to take measurements, found the first of these peaks. Later, the WMAP satellite and the Planck spacecraft measured these peaks much more precisely. Their findings supported the lambda CDM model of cosmology. Structure formation is the process that began shortly after the Big Bang, when small irregularities in the universe's density caused matter to collapse and form stars, galaxies, and groups of galaxies. Before this period, the universe was uniform, with no significant differences in density, as described by the Friedmann solutions to general relativity. Over time, tiny fluctuations in density started to grow and clump together, turning the smooth, featureless universe into a more complex structure filled with stars and galaxies. In the early stages, radiation dominated the universe and had a major impact on matter. This radiation prevented regular matter's density fluctuations from growing and forming structure. If the universe only had regular matter, these fluctuations would not have had enough time to evolve into the galaxies and groups we see today. The key to solving this problem lies in dark matter, which is not affected by radiation. This allowed its density changes to grow first, creating gravity wells that later helped normal matter collapse into galaxies and other structures. The gravitational pull from dark matter acted like a magnet, pulling in normal matter and speeding up the formation of these large cosmic structures. A striking example of the impact of dark matter is the bullet cluster, formed by the collision of 2 large galaxy clusters. What makes the bullet cluster particularly interesting is the difference between where the mass of the cluster is located according to gravitational lensing, the bending of light around massive objects, and where the visible matter is found. This difference is hard to explain with alternative gravity theories, which expect gravitational lensing to happen only around visible matter. However, the standard theory of dark matter can easily explain this. The visible gas in the clusters, which interacts with light and other forms of radiation, was slowed down and cooled by electromagnetic forces during the collision. Dark matter, on the other hand, doesn't interact with light in the same way, so it passes through the collision unaffected, separating from the visible gas. This created two separate lensing peaks, as seen. In addition to dark matter, astronomers use type Ia supernovae as standard candles to measure distances across the universe. These supernovae have a known brightness, so by measuring how dim they appear, scientists can calculate how far away they are. This method has shown that the universe is expanding faster and faster, a phenomenon usually explained by dark energy. Baryon acoustic oscillations, BAO, refer to regular changes in the density of normal matter, baryons, in the universe, which occurred on large scales in the early universe. These changes were caused by sound waves traveling through the hot, dense fluid of photons and baryons before the universe cooled enough for atoms to form. The effects of these sound waves can still be seen in the cosmic microwave background, CMB radiation. As the universe expanded, dark matter and normal matter began to clump together, but the effect of the original changes weakened over time. However, we can still observe a slight preference for galaxies to be separated by about 147 million light-years, which is a subtle but measurable signature of these early changes. This pattern was predicted in the 1990s and confirmed in 2005 through large galaxy surveys like the Sloan Digital Sky Survey and the 2DF Galaxy Redshift Survey. By combining CMB observations with BAO measurements, scientists can get a precise estimate of important cosmic values, such as the rate of expansion of the universe and the amount of matter it contains. These results support the lambda CDM model, which is the current leading theory of cosmology. Large surveys of galaxy redshifts can help us create a three-dimensional map of how galaxies are spread out in the universe. However, these maps are not perfect because the distances we estimate are based on the redshift we observe. The redshift we measure is affected by two things. The main factor is the universe's expansion, but there's also a smaller influence from the galaxy's own motion, known as its peculiar velocity. In general, superclusters, groups of many galaxies, are growing more slowly than the average expansion of the universe because their gravity is pulling things together. On the other hand, voids, vast empty spaces between galaxies, are expanding faster than the universe as a whole. This difference in expansion causes some interesting effects. For example, galaxies that are located in front of a supercluster are moving toward it faster than expected, so their redshift will be a little higher than we would normally calculate for their distance. Conversely, galaxies behind the supercluster appear to have a slightly lower redshift than expected. This difference causes superclusters to look flattened along the line of sight, while voids look stretched. However, this effect is hard to notice in a single structure, since we don't know its exact shape. Instead, scientists can observe this effect by averaging data from many structures. The phenomenon was first predicted by Nick Kaiser in 1987 and was later confirmed in 2001 by the 2DF Galaxy Redshift Survey, with results matching what we expect from the lambda CDM model of the universe. In a related field of study, the Lyman alpha forest refers to the collection of absorption lines found in the spectra of distant galaxies and quasars. These lines are caused by neutral hydrogen absorbing light at a specific wavelength, called the Lyman alpha transition. Observations of the Lyman alpha forest help astronomers test and refine cosmological models with results that align with findings from the WMAP data. Dark matter is often divided into three types: cold, warm, and hot. These names don't refer to temperature, but instead describe how fast the particles were moving in the early universe. In simple terms, they show how far the particles traveled due to random movements before the universe started expanding and slowing them down. This distance is called the free streaming length, FSL. The type of dark matter depends on how this FSL compares to the size of a protogalaxy, an early cosmic object that would later become a small galaxy. If the FSL is much smaller than the size of a protogalaxy, it's called cold dark matter. If it's about the same size, it's warm dark matter, and if the FSL is much larger, it's hot dark matter. Some theories suggest a mix of these types, which were more popular in the middle of the 1990s but became less favored after the discovery of dark energy. The key idea behind the free streaming length is that, after the Big Bang, the universe started with small changes in density caused by tiny quantum changes at the smallest levels. As these particles moved from denser areas to less dense ones, the fast expansion of the universe limited how far they could go. Faster particles, like those in hot dark matter, could travel further before the universe expanded too much, while slower particles, such as those in cold dark matter, couldn't move as far. This means that the free streaming length sets a limit on the size of structures that could form in the early universe. Hot dark matter would lead to the formation of large structures like superclusters, which would eventually break apart into galaxies. On the other hand, cold dark matter allows for smaller structures like galaxies to form first. Recent observations, especially deep field images of the universe, show that galaxies were the first to form, followed by clusters and superclusters as galaxies group together. This supports the idea that most dark matter is cold, not hot. This is also why neutrinos, which move almost at the speed of light and would be considered hot dark matter, cannot account for most dark matter. Dark matter refers to any type of matter that interacts with visible matter, like stars and planets, mainly through gravity. This means that dark matter might not be made of a completely new type of particle, but could, in theory, include regular matter like protons or neutrons. In fact, many objects familiar to astronomers, such as planets, brown dwarfs, red dwarfs, stars, white dwarfs, neutron stars, and black holes, fall into this category. For example, when a black hole pulls in matter, it doesn't differentiate between regular matter, like protons, and other kinds of matter. Once it's inside the event horizon, all matter is treated the same. These hard-to-detect objects are grouped together as machos, massive compact halo objects. Some scientists once thought that machos made up the majority of dark matter, but this idea has since been largely rejected. There is strong evidence suggesting that most of dark matter is not made up of regular visible matter. First, if there were enough regular matter like gas or dust scattered around, we would be able to see it when it's lit up by the light from stars. However, we don't see this kind of matter in the quantities we would expect. Next, the Big Bang theory helps us understand how the elements we observe today were created. According to this theory, if there were more normal matter, called baryons, in the early universe, we would have seen a higher abundance of elements like helium, lithium, and other heavier elements. Based on what we observe, we know that only about 4 to 5% of the universe's total mass consists of this regular matter. However, large-scale studies of galaxies and other cosmic structures show that the total amount of matter is about 30% of what is needed to keep the universe stable. Further investigations have shown that only a small portion of dark matter seems to be in the form of regular hidden objects, like small planets or black holes called machos. Studies involving the bending of light by gravity, gravitational microlensing, suggest that these objects can't account for the majority of dark matter, as their masses fall within a range that excludes nearly all of the plausible candidates. Detailed studies of the cosmic microwave background, the faint radiation left over from the Big Bang, by missions like WMAP and Planck, provide strong evidence that about 5/6 of the matter in the universe doesn't interact much with light or regular matter, except through gravity. This suggests that dark matter is largely invisible and can only be detected through its gravitational influence. If regular matter, called baryonic matter, doesn't account for most of dark matter, then dark matter must be made of something else, specifically non-baryonic matter. There are two main possibilities for non-baryonic dark matter: new mysterious particles and ancient black holes from the early universe. Unlike regular matter, these non-regular particles don't help create the elements that formed during the Big Bang, a process known as Big Bang nucleosynthesis. Instead, we only notice them because of the gravitational effects they cause, such as how they bend light, called weak lensing. Some types of dark matter can even interact with each other, self-interacting dark matter, or with normal particles like WIMPs, weakly interacting massive particles. These interactions might produce detectable signs, such as gamma rays and neutrinos, which scientists could possibly observe, indirect detection. There are many different candidates for dark matter, each with its own strengths and weaknesses. WIMPs don't have a strict definition, but they are generally thought of as elementary particles that interact through gravity and possibly other weak forces, such as the weak nuclear force. Many theories suggest that WIMPs were created in the early universe in a similar way to regular particles. These particles would make up what's called cold dark matter. To explain how much dark matter we have today, the WIMP particles would need to be able to destroy each other in a specific way, which matches what would happen if they had masses around 100 billion electron volts and interacted through the electroweak force. This idea is often called the WIMP miracle, because it fits so well with predictions from supersymmetric theories, which extend the standard model of particle physics. A stable partner particle from supersymmetry has long been seen as a prime candidate for dark matter. Researchers are working hard to find WIMPs by looking for the products of their destruction, such as gamma rays, neutrinos, and cosmic rays coming from nearby galaxies. They also use experiments designed to directly detect WIMPs in laboratories by measuring their interactions with atomic nuclei or by trying to create WIMPs in particle colliders like the Large Hadron Collider, LHC. However, in the early 2010s, experiments didn't find strong evidence for supersymmetry, and the LHC results cast doubt on the simplest WIMP ideas. Axions, another candidate for dark matter, are theoretical particles that were first proposed in 1978 by Frank Wilczek and Steven Weinberg. These particles were originally suggested to solve a problem in the theory of quantum chromodynamics, QCD, which explains how quarks and gluons interact. Axions are incredibly light and weakly interact with other particles, making them a perfect candidate for dark matter. They could be produced in the early universe and would remain present today, their abundance depending on their mass. Axions are thought to be so light that they could help explain some of the small-scale issues in the lambda CDM model, the leading cosmological model. The axion theory has gained traction in recent years, especially after WIMPs were not detected. The axion's extremely low mass means that quantum effects could potentially explain the small-scale mysteries of dark matter. Primordial black holes, another interesting idea, are thought to have formed in the very early universe, right after the Big Bang. During the period of rapid expansion known as inflation, incredibly dense regions of subatomic matter could have collapsed under their own gravity, creating black holes without the need for a star's death, as is the case with regular black holes. These black holes would predate the formation of the first stars and could have masses ranging from tiny, even as small as atoms, to incredibly large, far beyond typical stellar black holes. The concept of primordial black holes was first suggested in 1967 by Yakov Zeldovich and Igor Novikov, and later by Stephen Hawking in 1971. The idea quickly gained traction as a possible explanation for dark matter. One of the advantages of primordial black holes as dark matter candidates is that the theory behind black holes is already well established in physics, general relativity, and black holes themselves are already known to exist. However, creating primordial black holes might require complex conditions, such as exotic cosmic inflation or theories beyond the standard model of particle physics. In 2015, gravitational wave measurements from the detection of black hole mergers sparked renewed interest in primordial black holes as dark matter. Some black holes detected by these experiments had masses that seemed too large to be formed by the usual processes, like the collapse of a star. This suggested they could be primordial. However, a study that looked for signs of gravitational lensing from intermediate mass black holes, expected to be dark matter, found no evidence for them, although some researchers suggest this could be due to assumptions about the mass of these black holes. Further observations, like those made by the James Webb Space Telescope, may provide more clarity on this theory. Scientists once thought that incredibly small black holes, known as primordial black holes, might make up a significant portion of dark matter. However, the Voyager 1 spacecraft, which explored beyond the Sun's influence, measured the flow of positrons and electrons and found something surprising. The amount of particles detected was too low, and their energy levels were not what scientists expected. This led researchers to conclude that these tiny black holes are too rare to account for dark matter. Despite this, the idea of dense forms of dark matter continues to be researched. with new theories even suggesting ways to cool dark matter. As of 2018, the mystery remains unsolved. In 2019, further observations of the Andromeda Galaxy showed no signs of microlensing effects, which would be expected if tiny black holes were present, adding more doubt to their existence. However, there's still a gap in our understanding. There is a range of mass smaller than what we can currently detect with optical microlensing, where primordial black holes could potentially make up all of the dark matter. This area remains open for exploration and continues to challenge our understanding of the universe. If dark matter is made of particles that barely interact with anything, an important question arises. Could these particles form objects like planets, stars, or black holes? Historically, the answer has been no, and there are two key reasons for this. It can't easily lose energy. Regular matter forms dense objects like stars and planets because it can lose energy in many ways. For example, when particles fall inward due to gravity, they can lose energy, which allows them to slow down and condense into more stable objects. Dark matter, however, doesn't seem to have the ability to lose energy because it doesn't interact with other matter strongly, except through gravity. Without ways to release energy, dark matter particles that start to get pulled inward would just heat up, speed up, and eventually escape, preventing the formation of compact objects. It doesn't interact in diverse ways. Regular matter interacts through multiple forces, such as gravity, electromagnetism, and the strong nuclear force, allowing it to form complex structures like atoms, stars, and galaxies. For instance, inside stars, particles interact through nuclear fusion, emitting light and neutrinos. In dark matter, we don't see evidence for such interactions beyond gravity, and possibly some weak interactions, but this is still speculation. Without these varied interactions, dark matter doesn't have the ability to form the kinds of structures that regular matter does. If dark matter is composed of subatomic particles, these particles pass through every square centimeter of Earth millions or even billions of times every second. Many experiments are trying to test this idea. While WIMPs, weakly interacting massive particles, have been the most commonly searched for candidates, axions are also getting attention, especially with projects like the Axion Dark Matter Experiment, ADMX. Other possibilities include heavy particles from a hidden sector that only interact with regular matter through gravity. There are two main types of experiments investigating dark matter: direct detection experiments. These look for signs that dark matter particles are scattering off atomic nuclei in a detector. The goal is to measure tiny energy shifts, a few thousand electron volts, caused by these interactions. When dark matter hits an atom, the atom might release energy in the form of light or vibrations, which can be detected. To do this well, these experiments need to be as isolated as possible from background interference, which is why they are often conducted deep underground, where cosmic rays don't interfere. Notable underground labs include Stowell Mine, Sudan Mine, and the Gran Sasso National Laboratory. These experiments often use two technologies: cryogenic detectors that measure heat from particle collisions in materials like germanium, noble liquid detectors that detect light produced when a particle hits liquids like xenon or argon. Some well-known experiments in these areas include CDMS, CREST, xenon, and LUX. These detectors are especially good at telling dark matter apart from background particles, which mostly scatter off electrons, while dark matter particles scatter off atomic nuclei. Indirect detection experiments. These search for the effects of dark matter particles destroying each other or breaking down. There's currently no confirmed detection of dark matter in direct detection experiments, but these efforts have helped narrow down the possible properties of dark matter particles. One interesting claim comes from the Dharma NII and Dharma Libra collaborations, which have noticed a yearly change in their data, possibly due to the Earth's movement through the dark matter cloud. However, other experiments, such as LUX and super CDMs, have not seen the same effect, creating a bit of a mystery. There are also special experiments with directional sensitivity, which track the motion of dark matter particles based on the solar system's movement around the galactic center. This method tries to separate dark matter signals from background noise, which should be evenly spread out. These experiments, such as DMTPC and drift, try to detect the direction in which dark matter is moving to help find possible signals. Indirect detection experiments aim to find signs of dark matter by looking for the results when dark matter particles self-destruct or break down in space. In certain areas with high amounts of dark matter, like the center of the Milky Way, two dark matter particles might collide and destroy each other, releasing gamma rays or pairs of normal particles and their opposites, antiparticles. Alternatively, if a dark matter particle is unstable, it might break down into normal particles or others, which could be detected indirectly through an unexpected burst of gamma rays, antiprotons, or positrons coming from areas with a lot of dark matter, like the Milky Way's center or distant galaxies. One of the challenges of this kind of search is that other space events could produce similar signals, so multiple signals from different sources are needed to confirm a dark matter discovery. Dark matter particles that pass through the Sun or Earth might interact with atoms and lose energy in the process. This could cause dark matter to build up at the centers of these celestial bodies, increasing the chances for collisions or destruction. These events could send out a special signal of high-energy neutrinos, which could serve as strong evidence of dark matter made of WIMPs, weakly interacting massive particles. Instruments like Amanda, IceCube, and Antares are actively searching for this signal. In addition, the detection of gravitational waves by LIGO in 2015 opened the door for observing dark matter in new ways, especially if it exists as early black holes. Several experiments have tried to detect dark matter emissions, such as those from destruction or breakdown. For example, the Energetic Gamma Ray Experiment telescope spotted more gamma rays in 2008 than expected from the Milky Way, but scientists believed this was due to errors in estimating the telescope's sensitivity. The Fermi Gamma Ray Space Telescope is continuing this search, and in 2009 it observed a puzzling extra amount of gamma rays from the center of the Milky Way. This could be a sign of dark matter destruction or an unknown group of pulsars. In 2012, a deeper analysis of Fermi data suggested a 130 giga-electron-volts signal from the Milky Way's center, which was interpreted as a possible result of WIMP destruction. At even higher energies, ground-based telescopes have set limits on dark matter destruction in dwarf galaxies and galaxy groups. The Pamela experiment, launched in 2006, detected an unusual amount of positrons, which might come from dark matter or pulsars, though no similar excess of antiprotons was found. Similarly, the Alpha Magnetic Spectrometer aboard the International Space Station observed high-energy cosmic rays in 2013, possibly linked to dark matter destruction. Another approach to finding dark matter involves trying to create it in a laboratory. Experiments like those at the Large Hadron Collider, LHC, may detect dark matter particles formed during proton collisions. Since dark matter doesn't interact much with regular matter, it might be spotted indirectly by noticing large amounts of missing energy and momentum that escape detection, while other particles from the collision are measured. The LEP experiment, using a similar method but probing the interaction between dark matter and electrons, also provides limits on dark matter. Any discovery of dark matter in such experiments must be verified by findings from indirect or direct detection methods to confirm that the new particle is truly dark matter. Since dark matter has yet to be identified, many alternative theories have emerged to explain the same cosmic events. General relativity, the theory that supports much of the evidence for dark matter, is well tested on the scale of the solar system but hasn't been fully proven on galactic or cosmic scales. Some scientists suggest that changing general relativity could eliminate the need for dark matter. Well-known alternatives include MOND, modified Newtonian dynamics, TVS, a version of MOND, FR, gravity, negative mass, dark fluid, and entropic gravity, among others. A key challenge for these alternative theories is that the evidence for dark matter comes from many independent sources. While it might be possible to explain a single observation, explaining all the evidence without dark matter is very difficult. Still, some alternatives have had limited success, like the 2016 test of gravitational lensing in entropic gravity and a 2020 measurement supporting MOND. Despite these successes, most astrophysicists believe that while changes to general relativity could explain some of the observations, the overall data suggests that dark matter must exist in some form. When we think about the origin of the universe, the question that often comes to mind is, what was there before anything existed? How did everything come into being from what seems like nothing? This question has puzzled scientists, philosophers, and thinkers for centuries, and it touches upon one of the most profound mysteries of existence. At the heart of this enigma is the concept of nothingness, a void, an emptiness, a vacuum that existed long before atoms, stars, and galaxies came into being. But the story of this nothingness is far more complex and fascinating than we might first imagine. This nothingness is not merely an absence of matter, it is a peculiar state that has the potential to create everything we know. Before diving into the paradoxes surrounding nothingness, it's essential to understand what we mean by the term nothing. In our everyday lives, nothing seems like an easy concept to grasp. If you have an empty room, you might think that there is nothing in it. But even in this case, the room is filled with air, light, and the potential to hold something else. The nothing that cosmologists refer to is not this simple emptiness. Instead, it is a state devoid of any matter, energy, or even space itself. It's a true void, a state of absolute nothingness. Now let's imagine a time before the birth of the universe. There were no stars, no planets, no atoms, and not even the space that we think of today. In fact, the very concept of space didn't exist in the way we understand it. It was a moment before the Big Bang, a time when the laws of physics as we know them didn't operate in the same way. At this point, everything we consider something was still to be created. So, what was this nothingness like? Was it truly empty, or was there something more subtle and strange happening in the void? According to modern physics, this emptiness wasn't as inert as it may seem. In fact, this vacuum of nothingness may have been the birthplace of all the matter, energy, and forces that make up our universe today. The question of how something can come from nothing is often described as a paradox. If there was nothing, how could anything possibly come into existence? It seems to defy all logic and common sense. But modern science, particularly quantum mechanics, offers a surprising answer. In the world of quantum physics, nothing is not truly empty. Even in a vacuum, there is a strange and mysterious activity taking place. This activity is known as quantum fluctuations. Quantum fluctuations are tiny, unpredictable changes in the energy of empty space. These fluctuations are brief, momentary bursts of energy that can briefly appear out of nothing and then disappear. While these energy fluctuations are incredibly small and short-lived, they are real and measurable. These fluctuations suggest that even in a true vacuum, where no particles are present, there is still a kind of activity occurring on the smallest scales. This is not something we can observe with our naked eyes, but it is a phenomenon that can be detected and understood through the principles of quantum mechanics. Now let's bring this back to the creation of the universe. The Big Bang, which is thought to have occurred about 13.8 billion years ago, was not an explosion in space. It was an expansion of space itself. At the very beginning, all the energy and matter that would eventually form the universe were concentrated in an incredibly hot, dense point known as a singularity. But how did this singularity come to be? And how did it come from nothing? Some scientists propose that the energy fluctuations in the quantum vacuum could have triggered the Big Bang. Essentially, the vacuum of nothingness decided to shake things up and create particles, energy, and eventually the entire universe. This process is known as quantum creation. It suggests that space itself can fluctuate, and in the right conditions, these fluctuations could give rise to the creation of matter and energy. In this way, the laws of physics that govern the behavior of particles and energy in our universe could have emerged from the very nothingness that existed before. This idea leads to a fascinating possibility. Perhaps the entire universe, everything we see around us, from the smallest particles to the vastest galaxies, was born out of a quantum fluctuation in the vacuum of nothingness. In this view, the creation of the universe wasn't a single event, but rather the ongoing result of these fluctuations in the fabric of space-time. So if the universe emerged from nothing, how do the laws of physics come into play? How is it possible for the universe to obey consistent rules if it was created from a void, from a state where no laws of physics existed? This question challenges our understanding of how the universe works, but it is here that the elegance of science comes into focus. One key idea to understand is that the laws of physics themselves are not arbitrary. They arise from the fundamental properties of the universe. When we talk about the laws of physics, we are referring to the principles that govern the behavior of matter and energy. These laws include the force of gravity, the interactions between subatomic particles, and the principles of thermodynamics. But where did these laws come from? How did they emerge from nothingness? According to current scientific theories, the laws of physics might not have been fixed in the way they are today at the time of the Big Bang. In the very early moments of the universe, shortly after the Big Bang, the laws of physics may have been vastly different. For example, it is thought that the universe underwent a period of rapid expansion known as inflation. During this time, space itself expanded exponentially, and the fundamental forces that govern the universe, gravity, electromagnetism, and the strong and weak nuclear forces, may not have been distinct from one another. In the extremely high-energy environment of the early universe, these forces might have been unified into a single force, a superforce, that gradually separated as the universe cooled. The idea that the laws of physics could change over time is a mind-boggling one, but it is supported by the observations and mathematical models developed by scientists. As the universe cooled and expanded, the conditions changed, and the forces that govern the behavior of matter began to take on their current form. It's as though the universe started with a set of very simple, very general principles that slowly grew into the complex web of laws that govern everything we know today. In this way, the universe could have evolved from the simplest of beginnings, a quantum fluctuation in the vacuum, into the highly structured and orderly system that we observe. The laws of physics that we take for granted today were not imposed from outside the universe. Instead, they are inherent in the very fabric of space-time, emerging naturally from the conditions that arose in the aftermath of the Big Bang. The quantum vacuum, which is often called empty space, is not as empty as it might seem. It is, in fact, teeming with potential. At the most fundamental level, space is filled with quantum fields that stretch throughout the entire universe. These fields are the building blocks of matter and energy, and they are responsible for the creation of particles, the propagation of forces, and the very existence of space-time itself. Even when there is no matter or energy present, these quantum fields are still active. They interact with one another, fluctuating with energy, even in the absence of any visible particles. This activity is what gives rise to the mysterious phenomena of quantum mechanics, such as particle-antiparticle pairs that appear and vanish in an instant. The concept of a quantum vacuum also challenges our traditional understanding of empty space. In classical physics, empty space was thought to be a void, a complete absence of anything. But in the quantum world, empty space is anything but empty. It is a dynamic, ever-changing field of energy and possibility. In a sense, the quantum vacuum is the source of all creation. It holds within it the potential for all the particles, forces, and structures that make up our universe. The vacuum is not just a passive emptiness, it is a seedbed of creation, where anything can potentially arise from the fluctuations in energy and the interactions of quantum fields. Quarks are the smallest known particles in physics. Unlike atoms or molecules, which we can see through microscopes, quarks are so tiny that they cannot be observed directly. Instead, scientists study them through powerful experiments using particle accelerators, which smash atoms together at incredible speeds to reveal their inner components. Quarks belong to a category of particles called elementary particles. This means they are not made of anything smaller, at least based on our current understanding of physics. Scientists believe that quarks are the fundamental building blocks of protons and neutrons, which make up the nucleus of an atom. A key feature of quarks is that they never exist alone. Instead, they always come together to form larger particles. This is because they are held together by a powerful force known as the strong nuclear force, one of the 4 fundamental forces of nature. Quarks come in 6 different types or flavors. These flavors have unusual names, but each plays a role in the structure of the universe. Up quark, down quark, charm quark, strange quark, top quark, and bottom quark. The up and down quarks are the most common because they form the protons and neutrons found in everyday atoms. The other 4 quarks, charm, strange, top, and bottom, are rarer and are usually found in high-energy environments, such as those created during particle collisions in laboratories or in the intense conditions of the early universe. Each quark has a specific charge, which determines how it interacts with other particles. Up quarks have a charge of positive 2/3, while down quarks have a charge of negative 1/3. The combination of these charges is what gives protons and neutrons their overall electrical charge. Atoms are made up of three main components: protons, positively charged particles; neutrons, neutral particles with no charge; and electrons, negatively charged particles that orbit the nucleus. Quarks are responsible for forming the first two, protons and neutrons, which reside in the center of an atom, known as the nucleus. Each proton is made of two up quarks and one down quark. Each neutron is made of two down quarks and one up quark. These quarks are held together by another type of particle called a gluon. Gluons act like an invisible force that glues quarks together, ensuring that protons and neutrons remain stable. This force is incredibly strong, far stronger than the force of gravity or electromagnetism, which is why protons and neutrons stay tightly packed inside the nucleus of an atom. Electrons, on the other hand, are not made of quarks. Instead, they belong to a separate group of particles known as leptons. Despite this difference, electrons play a crucial role in atoms by orbiting around the nucleus, creating the structure that allows atoms to interact and form molecules. The story of quarks begins at the very birth of the universe, during the Big Bang, which happened approximately 13,800,000,000 years ago. At the moment of the Big Bang, the universe was an unimaginably hot and dense sea of energy. In the first trillionth of a second, the energy cooled enough to allow quarks to form. These quarks existed freely for a very brief moment before the strong nuclear force pulled them together to form the first protons and neutrons. As the universe continued to expand and cool over the next few minutes, these protons and neutrons combined to form the first atomic nuclei. However, it took another 380,000 years before the universe cooled enough for electrons to join the nuclei, forming the first complete atoms, mostly hydrogen and helium. Over billions of years, these atoms came together to form stars, planets, and eventually everything we see today. For many years, scientists believed that protons and neutrons were the smallest building blocks of matter. However, in the 1960s, physicists Murray Gell-Mann and George Zweig proposed that these particles were actually made of even smaller components, what we now call quarks. Their idea was later confirmed through high-energy experiments in particle accelerators, which smashed protons and neutrons together and revealed their inner structure. Today, scientists continue to study quarks using advanced machines like the Large Hadron Collider, the most powerful particle accelerator in the world. One of the most exciting discoveries was made in 1995, when scientists at the Fermilab laboratory finally detected the top quark, the last missing piece of the quark family. Quarks are not just tiny particles hidden inside atoms, they are the very foundation of matter. Quarks are also essential for understanding nuclear energy, which powers the sun and provides electricity through nuclear reactors. Additionally, the study of quarks has led to important discoveries in medicine, technology, and space exploration. Quarks can never be alone. Unlike electrons, which can move freely, quarks always exist in groups. This is due to a unique property called confinement. Quarks have color charges. Even though they are too small to have actual colors, physicists describe them using color terms like red, green, and blue to explain how they interact. The top quark is incredibly heavy. In fact, it is about as heavy as a gold atom, even though it is much smaller than a proton. Quarks exist in exotic particles. While protons and neutrons are the most common particles made of quarks, scientists have discovered others like pions, kaons, and tetraquarks, which behave in strange and unexpected ways. Gluons act as the glue that holds quarks together. They are responsible for transmitting the strong nuclear force, one of the four fundamental forces of nature. Without gluons, quarks would not be able to form protons or neutrons, meaning atoms, and everything made of atoms, would not exist. Immediately after the Big Bang, the universe was unimaginably hot and dense. Scientists estimate that within the first fraction of a second, less than a trillionth of a second, the entire universe was a seething soup of quarks and gluons, known as quark-gluon plasma. This state of matter was unlike anything we experience today. The temperature was more than 1 trillion degrees Celsius, hotter than the core of any star. At such extreme temperatures, quarks and gluons were free, meaning they did not yet form protons, neutrons, or any other stable particles. Instead, they constantly collided, combined, and broke apart in an incredibly fast and energetic process. As the temperature dropped below a certain point, around a few trillion degrees, quarks and gluons started sticking together. This process is known as hadronization. During hadronization, quarks combined in specific ways to form larger particles known as hadrons. The most important hadrons for the development of the universe were protons, which consist of 2 up quarks and 1 down quark; neutrons, which consist of 2 down quarks and 1 up quark. This stage of the universe's evolution was crucial. Without it, the fundamental ingredients needed for atoms would never have formed. The collisions between quarks and gluons during this time were incredibly energetic, shaping how matter emerged. The strong force carried by gluons ensured that quarks were bound together tightly. Even when the universe continued to expand and cool further, the bonds between quarks remained intact, leading to the formation of atomic nuclei. One of the most important forces at play in these early interactions was the strong nuclear force. Unlike gravity, which pulls objects together over large distances, or electromagnetism, which affects charged particles, the strong force only works at incredibly short distances, inside atomic nuclei. The strong force, carried by gluons, is so powerful that it prevents quarks from ever being isolated. This is why we never observe free quarks in nature. Instead, they are always found inside larger composite particles like protons and neutrons. Think of gluons as an invisible force field that binds quarks together, similar to how a powerful magnet keeps metal objects stuck together. The difference is that the strong force is much stronger than magnetism, so strong that it even overcomes the repulsion between positively charged protons inside atomic nuclei. Once quarks and gluons had settled into protons and neutrons, the universe continued to expand and cool. This allowed protons and neutrons to come together through nuclear fusion, forming the first atomic nuclei. At this stage, the universe was still a hot and dense plasma of charged particles, meaning electrons had not yet settled into stable orbits around nuclei. But as the temperature dropped further, electrons were finally able to attach to nuclei, creating the first neutral atoms. This process, known as recombination, occurred approximately 380,000 years after the Big Bang and marked the beginning of the universe as we know it. With stable atoms now in existence, light could travel freely for the first time. This event led to the formation of the cosmic microwave background radiation, which scientists can still detect today as a faint glow across the universe. Understanding how quarks and gluons behaved in the early universe is not just a theoretical exercise. Scientists have been able to recreate conditions similar to the quark-gluon plasma in high-energy particle colliders, such as the Large Hadron Collider, LHC, in Switzerland, and the Relativistic Heavy Ion Collider, RHIC, in the United States. By smashing heavy atomic nuclei, such as gold or lead, at nearly the speed of light, scientists can generate temperatures high enough to briefly produce quark-gluon plasma. These experiments allow researchers to study how quarks and gluons interact, providing deeper insights into the universe's first moments. Through these studies, scientists have confirmed that quark-gluon plasma behaves like an almost perfect fluid, meaning it flows with almost no resistance. This discovery has helped refine our understanding of the fundamental forces that shape the cosmos. The collisions and interactions of quarks and gluons in the early universe played a fundamental role in shaping everything we see today. If these tiny particles had not combined in the precise ways they did, the universe would be unrecognizable. There would be no protons, neutrons, or atoms, meaning no stars, planets, or life itself. By studying quarks and gluons, scientists gain a better understanding of the fundamental nature of matter. These particles, which once existed freely in the high-energy chaos of the early universe, are now confined within the stable matter that makes up the entire cosmos. Quark confinement is a strange rule of nature. No one has ever seen a quark by itself. Unlike electrons, which can exist freely, quarks are always found in groups. They combine in sets of 3 to form protons and neutrons, or in pairs to create particles called mesons. This happens because of a force so strong that trying to separate quarks only makes them pull back together even harder. This force is known as the strong nuclear force, and it is the most powerful fundamental force in nature, far stronger than gravity or even electromagnetism. To understand this, imagine two quarks connected by a rubber band. If you pull them apart, the rubber band stretches and stores more energy, but instead of snapping like a normal rubber band would, the energy transforms into new quarks and antiquarks, which immediately form new particles. This is why quarks never exist alone. They are always confined within larger particles. Billions of years ago, in the moments after the Big Bang, the universe was unimaginably hot and filled with energy. During this time, quarks moved freely, like water molecules in steam. But as the universe expanded and cooled, quarks started sticking together, bound by the strong nuclear force. At first, they formed combinations of three, creating protons and neutrons. Protons consist of two up quarks and one down quark, while neutrons contain two down quarks and one up quark. The force that holds these quarks together is so strong that no natural process can break them apart. This was the birth of the particles that would later form atomic nuclei, the heart of every atom in the universe. Without quark confinement, protons and neutrons would not exist, and without them, atoms could never have formed. That means there would be no elements, no molecules, and no life as we know it. The strong force that traps quarks inside protons and neutrons also works on a larger scale, holding protons and neutrons together inside atomic nuclei. Without it, atomic nuclei would fly apart because of the repulsion between positively charged protons. This force, carried by particles called gluons, acts like an invisible rope, ensuring that protons and neutrons remain tightly packed together. Scientists have spent decades trying to fully understand quark confinement. The theory that explains it is called quantum chromodynamics, QCD. According to QCD, quarks carry a type of color charge, much like electric charge. But instead of positive and negative, there are three types: red, green, and blue. The strong force ensures that quarks always combine in a way that their colors cancel out, keeping them forever confined. Time is one of the most mysterious and essential aspects of our universe. It is an invisible force that allows everything to happen in a sequence, one event following another. Without time, the world as we know it could not function. Imagine throwing a ball. Without time, the ball would never move. It would stay frozen in place, unable to travel through the air or fall to the ground. Similarly, when we cook food, it changes from raw to cooked over a period. This transformation is only possible because time allows change to happen. Every action, from the smallest movement to the grandest cosmic event, depends on the flow of time. Now, imagine a world where time doesn't exist. Could anything still be created? Could anything move or change? Would the universe even be possible? To answer these questions, let's look at how the universe itself began. Scientists believe that everything started with an enormous explosion called the Big Bang, which happened about 14 billion years ago. In those first few moments, there was no structure, no galaxies, no stars, just an unimaginably hot and chaotic ocean of pure energy. But as the universe expanded and cooled, this energy started changing into matter. Tiny subatomic particles, so small that they cannot even be seen, began to appear. Eventually, these particles joined together to form the first atoms, mostly hydrogen and helium, which are the simplest and lightest elements in the universe. But here's the key point. This entire process took place over time. If time didn't exist, then the universe would have remained in a frozen, unchanging state. There would be no moments passing, no cooling, no combining of particles. Atoms, the very building blocks of everything we see, could never have formed. To understand this better, imagine you are trying to build a house. You have all the materials, bricks, cement, wood, but every moment is completely frozen. You cannot pick up the bricks, you cannot place them together, and you cannot shape anything. Since there is no movement, no sequence of actions, the house can never be built. This is exactly what would happen in a universe without time. Without time, nothing can change. Without change, nothing new can form. The same rule applies to the birth of atoms. For an atom to form, particles must interact and combine. This process requires movement and change can only happen if time is passing. Some scientists and philosophers have asked whether time is a real part of the universe or just something that humans created to make sense of their surroundings. Could the universe exist outside of time? Could time itself be an illusion? Certain scientific theories suggest that in the earliest moments of the universe, before the Big Bang, time might not have existed in the way we understand it today. Some researchers believe that time could have emerged along with space and matter, meaning there was once a state where time, as we experience it, did not yet exist. But if this is true, then how did anything happen? How did the universe go from nothing to something? If time did not exist at all, then the universe would be stuck in a state of eternal stillness. Nothing would ever change. The universe would be frozen in an unchanging moment forever. Atoms, planets, stars. None of these could have come into being because their formation requires movement and interaction. Everything we know, from the way planets orbit stars to the way we grow older, happens because time moves forward. Without time, there would be no past, no future, only a single unchanging instant. Space and matter are deeply connected. The expansion of the universe created more space, but that space was not empty. It was filled with high-energy particles and radiation. As the universe expanded and cooled, the forces of nature started to shape matter. One of these forces, the strong nuclear force, is responsible for holding the centers of atoms together. Without it, protons and neutrons would not have bonded to form atomic nuclei. Another important force, electromagnetism, is what keeps electrons orbiting around the nucleus instead of flying off into space. These forces existed before atoms formed, but they could only start working once space had expanded enough and temperatures had dropped to a manageable level. This tells us that space was essential for atoms to form. Without space, there would have been no room for particles to move, interact, and eventually combine into stable atoms. Space provided the stage where these forces could act, bringing order to the early chaos of the universe. Imagine a universe without space, one where everything is squeezed together with no room to move. In such a universe, atoms as we know them could not exist. The subatomic particles that make up atoms need space to interact with each other. If they were trapped in an infinitely small point, they would be unable to form the structures we recognize as atoms. In physics, there is a concept called a singularity, which is a point where space and time break down. Scientists believe that before the Big Bang, the entire universe was in a singularity, a state of infinite density where normal physical laws did not apply. This means that, in a sense, atoms did not just need space to form, they needed space to exist at all. The moment space expanded, it created the conditions necessary for atoms to take shape and begin their journey toward forming everything we see today. One of the most mind-bending ideas in modern physics is that space is not just an empty void. Instead, it is an active part of the universe that can stretch, bend, and even ripple. Albert Einstein's theory of general relativity showed that space and time are woven together into something called space-time, and this fabric of reality is influenced by the presence of matter. In other words, matter, which is made of atoms, and space influence each other. Large amounts of matter, like stars and planets, warp the space around them, creating what we experience as gravity. This means that atoms did not just need space to form, atoms also shape space in return. This relationship between space and matter is one of the reasons why the universe continues to expand. As galaxies move apart, new space is created between them. This expansion ensures that there is always room for more atoms to interact, combine, and create new structures. Antimatter is a fascinating and mysterious type of material that is essentially the mirror image of ordinary matter. It is made up of special particles called antiparticles, which are like the twin opposites of the particles that make up everything around us. The main difference between matter and antimatter is that antimatter has reversed properties. Its electric charge, how it interacts with forces, and even how it behaves over time follow an opposite pattern. Scientists refer to this as CPT reversal, charge, parity, and time. Even though antimatter sounds like something out of science fiction, it actually exists in nature. It appears in powerful cosmic events, such as high-energy collisions between cosmic rays in space, and it can also be produced during certain types of radioactive decay. However, these natural occurrences only create minuscule amounts, and most antimatter vanishes almost instantly upon coming into contact with normal matter. Scientists have successfully created tiny amounts of antimatter in highly controlled laboratory conditions, particularly inside particle accelerators, large machines designed to smash subatomic particles together at incredible speeds. But even with all of our advanced technology, humanity has only been able to produce a few billionths of a gram of antimatter. One major reason is that antimatter is extremely difficult and expensive to create, store, and study. Unlike ordinary matter, which can be easily contained in solid or liquid form, antimatter must be trapped using magnetic and electric fields to prevent it from touching normal matter, because if it does, both instantly annihilate in a burst of energy. Despite its rarity, antimatter plays a crucial role in modern science and medicine. For example, in positron emission tomography, PET scans, a form of medical imaging, antimatter helps doctors detect and diagnose diseases, including cancer. It is also used in certain types of radiation therapy to treat tumors. Additionally, industries use antimatter for specialized imaging techniques. When an antiparticle meets its matching normal particle, something extraordinary happens. Both are destroyed in a powerful event called annihilation. This process releases a massive burst of energy, mostly in the form of gamma rays, a high-energy type of light, and sometimes additional subatomic particles. The amount of energy released depends on the total mass of the colliding matter and antimatter, following Einstein's famous equation E equals sign mc2, which states that mass can be converted into energy. If large amounts of antimatter were somehow collected and controlled, it could be the most efficient energy source imaginable. Just a small amount could, in theory, power entire cities or fuel spacecraft for interstellar travel. However, the immense cost and difficulty of creating and storing antimatter make such possibilities purely theoretical for now. Scientists believe that when the universe first formed, there should have been equal amounts of matter and antimatter. But strangely, the observable universe is made almost entirely of normal matter, with very little antimatter to be found. This puzzling imbalance is one of the greatest unsolved mysteries in physics, known as baryogenesis. If antimatter and matter were created in equal amounts, why didn't they annihilate each other completely? What caused the universe to favor matter over antimatter? Researchers are still searching for answers. Just as protons and electrons combine to form atoms in normal matter, their antiparticle counterparts, antiprotons and positrons, can combine to form antiatoms. The simplest of these is antihydrogen, which is made up of a positron orbiting an antiproton, just like a hydrogen atom in regular matter. Scientists have successfully created antihydrogen in laboratories, and they have even produced slightly more complex antihelium nuclei. These discoveries suggest that, in theory, entire elements of antimatter could exist. Before antimatter was formally understood, some scientists speculated about the existence of negative matter, a strange form of matter that would have negative mass and perhaps even reverse gravity. In the 1880s, a researcher named William Hicks explored the idea of negative gravity within a theory of swirling cosmic vortices. Later, in the 1890s, Carl Pearson introduced the concept of squirts and sinks in ether theory, where normal matter flowed out of some regions of space while negative matter was sucked in elsewhere. However, these ideas have since been abandoned as modern physics developed more accurate explanations of matter, energy, and forces. The term antimatter was first introduced by a scientist named Arthur Schuster in the year 1898. He mentioned it in 2 playful letters he sent to the scientific journal Nature. In his letters, Schuster speculated about the existence of antiatoms, atoms that would be the opposite of regular atoms. He even imagined entire solar systems made of antimatter. More interestingly, he proposed that if matter and antimatter were to come into contact, they would completely destroy each other. However, his ideas were not based on any solid scientific evidence, just curiosity and imagination. Additionally, his version of antimatter was different from what scientists later discovered because he thought it would have negative gravity, meaning it would fall up instead of down. The modern understanding of antimatter began in 1928 with a groundbreaking scientific paper written by Paul Dirac. Dirac was working on a mathematical equation that described the behavior of electrons, the tiny negatively charged particles found inside atoms. His equation unexpectedly suggested that a mirror image version of electrons, anti-electrons, could exist. However, even though his own work pointed in this direction, Dirac didn't immediately grasp the full meaning of his discovery. It was another famous physicist, J. Robert Oppenheimer, who took Dirac's equation and correctly interpreted what it meant. In his 1930 paper titled On the Theory of Electrons and Protons, Oppenheimer argued that there had to be a positively charged version of the electron, what we now call a positron. Since it had to have exactly the same mass as an electron, it could not be a proton, which is much heavier. Dirac later expanded on this idea in a 1931 paper, where he officially described positrons as anti-electrons. Just 1 year later, in 1932, a scientist named Carl D. Anderson actually discovered positrons in cosmic rays, high-energy particles coming from space. Anderson was the one who gave them the name positrons, which simply means positive electrons. Interestingly, while Dirac himself never used the word antimatter, the term naturally followed from the idea of anti-electrons, antiprotons, and other similar particles. Around the same time, in 1929, a scientist named Charles Janet imagined what an entire periodic table of antimatter elements might look like. In modern physics, there is an interesting idea known as the Feynman-Stuckelberg interpretation. According to this theory, antimatter behaves just like normal matter, except that it moves backward in time. This concept is widely used today in physics, especially in Feynman diagrams, which are visual tools used to study how tiny particles interact. Physicists have special ways of representing antimatter. One common method is to place a small bar over a particle's symbol. For example, a proton is written as P, while an antiproton is written as P. The same logic applies to the building blocks of these particles, called quarks. A proton is made up of 3 quarks, specifically 2 up quarks and 1 down quark. In contrast, an antiproton is made of 2 anti-up quarks and 1 anti-down quark. Another way to distinguish matter from antimatter is by looking at electric charge. A normal electron, which has a negative charge, is written as E, while a positron, which has a positive charge, is written as E+. To keep things clear, scientists never mix these 2 different notations. One of the biggest questions about antimatter was whether it behaved differently from normal matter when exposed to gravity. Some people once speculated that antimatter might fall upward instead of downward. However, recent experiments have proven that this is not true. In a fascinating study, scientists created a thin, extremely cold gas made up of thousands of antihydrogen atoms, a type of antimatter version of hydrogen. They trapped these antimatter atoms inside a vertical tube using strong electromagnetic fields generated by superconducting magnets. This setup created a magnetic bottle that prevented the antimatter from coming into contact with normal matter and annihilating. To test how antimatter behaved under gravity, the scientists gradually weakened the magnetic fields and let the anti-atoms escape. They used 2 special sensors to track the motion of these particles. The results were clear. Most of the anti-atoms exited from the bottom of the container, while only about 1/4 of them escaped from the top. This confirmed that antimatter falls down, just like regular matter, meaning there is no difference in their gravitational behavior. There are many strong theoretical reasons to believe that apart from having opposite charges, matter and antimatter are almost identical in every other way. In simple terms, if you were to create an entire antimatter universe, it would look and behave exactly like our own, except with all charges flipped. This means that an antiparticle must have the same mass and the same lifespan as its corresponding normal particle. One particularly mind-blowing idea is that antimatter stars, sometimes called anti-stars, could exist somewhere in the universe. If such a star were found, it would shine exactly the same way as a normal star made of matter. To test this idea, in 2016, scientists working on the ALPHA experiment studied antihydrogen atoms and measured the way they transitioned between their 2 lowest energy states. Their results were identical to those of regular hydrogen atoms, proving that quantum mechanics applies to antimatter just as it does to normal matter. From what we can see in the universe, almost everything around us seems to be made of regular matter instead of antimatter. If there were large regions of space dominated by antimatter, we would expect to see a powerful signal coming from the edges where matter and antimatter meet. This signal would come in the form of high-energy gamma rays created when the 2 types of particles collide and destroy each other. Scientists have not detected such signals, suggesting that our universe is overwhelmingly made up of matter. Antimatter is not completely absent, though. It is constantly being formed in places where extremely energetic particle collisions occur. For example, when high-speed cosmic rays crash into Earth's atmosphere, they create tiny amounts of antimatter in the form of antiparticles. However, these antiparticles do not last long, as they quickly collide with normal matter and vanish in a burst of energy. Similar processes happen in space, especially in places where powerful cosmic events occur, like the supermassive black hole at the center of our galaxy, the Milky Way. When antimatter is created and then destroyed, it releases gamma rays with a very specific energy, 511,000 electron volts, equivalent to the rest mass energy of an electron. One of the most mysterious findings about antimatter comes from a massive cloud of it floating near the heart of our galaxy. The European Space Agency's Integral satellite has observed this cloud, which appears to be unevenly spread out, matching the locations of certain X-ray emitting star systems. These systems often contain either black holes or neutron stars. Scientists believe that as normal matter falls into these extreme objects, it gains immense amounts of energy, leading to the production of antimatter in the form of electron-positron pairs. However, the exact details of how this happens remain unclear. Some scientists think that in the far reaches of the universe, entire galaxies made mostly of antimatter might exist. If they do, they would look just like regular galaxies, because antimatter follows the same physical and chemical rules as matter. This means that their stars, planets, and other celestial objects would emit and absorb light in the same way, making them nearly impossible to distinguish from normal galaxies. NASA is currently trying to find out if these antimatter galaxies exist by searching for the telltale gamma ray signals that would be produced if antimatter and matter ever collided in deep space. In October of the year 2017, a major breakthrough occurred in the study of antimatter. Scientists at CERN, working on an experiment called BASE, made an incredibly precise measurement of the magnetic properties of the antiproton. Their results showed that the magnetic moment of the antiproton matched that of the proton with astonishing accuracy, down to 1.5 parts per billion. This finding supports the idea that the universe obeys a fundamental principle called CPT symmetry, which suggests that the laws of physics should be the same for matter and antimatter. Notably, this was the first time that a property of antimatter had been measured more precisely than its matter counterpart. Another major milestone in antimatter research happened in the year 2018, when scientists in Italy successfully demonstrated antimatter quantum interference. This experiment, conducted at the Positron Laboratory in Como, was led by researcher Marco Giammaci. It provided new insights into how antimatter behaves at the quantum level, which could have important implications for our understanding of physics. Antimatter is not only found in deep space or high-energy physics experiments. It is also naturally produced on Earth in several ways. Some radioactive elements, like potassium-40, release positrons during their natural decay process. Additionally, when high-energy gamma rays interact with matter, they can create positrons. Another type of antimatter particle, called an antineutrino, is generated during a different kind of radioactive decay known as beta decay. Cosmic rays, which constantly bombard Earth, also contain various antiparticles. A fascinating discovery in the year 2011 revealed that antimatter is even produced in Earth's atmosphere. Researchers from the American Astronomical Society found that thunderstorms can generate positrons. This happens when intense electric fields within storm clouds accelerate electrons to nearly the speed of light, creating flashes of gamma rays. These gamma rays then interact with the atmosphere, leading to the production of antimatter. This unexpected finding suggests that even common weather phenomena can create antimatter under the right conditions. Another surprising source of antimatter is found in space close to Earth. In the Van Allen radiation belts, two giant zones of charged particles trapped by Earth's magnetic field, scientists detected antiprotons. The Pamela spacecraft, which studies cosmic rays, confirmed the existence of these antiprotons, suggesting that antimatter can exist in stable forms even near our planet. Antimatter can also form in any place where the temperature is extremely high, hot enough to provide the energy needed for matter and antimatter pairs to emerge. Scientists believe that in the earliest moments of the universe, during a period called baryogenesis, matter and antimatter were constantly being created and annihilated. However, today we see that the universe is dominated by matter, with almost no remaining antimatter. This imbalance, known as Baryon asymmetry, remains one of the biggest unsolved mysteries in physics. Scientists suspect that this imbalance may be linked to a phenomenon called CP symmetry violation, which has been observed in certain subatomic interactions. Understanding why this imbalance exists could help explain why the universe as we know it even exists at all. Recent astronomical observations suggest that extreme cosmic events, such as the formation of black holes and neutron stars, generate massive amounts of positron-electron plasma. These exotic particles are ejected into space at incredible speeds, forming high-energy jets that stretch for vast distances. These findings continue to add to the mystery of antimatter and its role in the universe, pushing scientists to search for more answers about this elusive and fascinating aspect of nature. From everything we can observe in the universe, it seems that almost everything around us is made of regular matter instead of its mysterious opposite, antimatter. If there were large sections of space where antimatter dominated, scientists would expect to see powerful energy bursts at the boundaries where matter and antimatter meet. This is because when these two types of particles collide, they instantly destroy each other, releasing intense radiation in the form of high-energy gamma rays. However, no such signals have been detected, which strongly suggests that nearly everything in our universe is made up of ordinary matter. That being said, antimatter is not completely absent. It is constantly being created in places where incredibly powerful particle collisions occur. One example is when high-speed cosmic rays crash into Earth's atmosphere. These collisions produce tiny amounts of antimatter in the form of antiparticles. However, these antiparticles do not last long. As soon as they encounter regular matter, they vanish in an instant, releasing energy in the process. A similar process happens in space, especially near the most energetic places in the universe, such as the supermassive black hole at the center of our galaxy, the Milky Way. When antimatter is created and then destroyed, it gives off gamma rays with a very precise energy level, 511,000 electron volts, which matches the energy of an electron's mass. One of the most puzzling discoveries about antimatter is the presence of a massive cloud of it floating near the center of our galaxy. Scientists have studied this cloud using the European Space Agency's integral satellite. Interestingly, the antimatter cloud does not seem to be evenly spread out. Instead, it matches the locations of certain X-ray emitting star systems, most of which contain either neutron stars or black holes. Scientists think that as normal matter falls into these powerful objects, it gains enormous amounts of energy, which then leads to the formation of antimatter in the form of electron-positron pairs. However, exactly how this process works is still not fully understood. Some researchers believe that in the vast stretches of the universe, there could be entire galaxies made mostly of antimatter. If they exist, they would look almost identical to the galaxies made of normal matter. This is because antimatter follows the same physical and chemical rules as regular matter. The stars, planets, and other celestial bodies in these galaxies would emit and absorb light in the same way, making them nearly impossible to distinguish from ordinary galaxies. Scientists at NASA are currently searching for these antimatter galaxies by looking for the special gamma-ray signals that would appear if antimatter and matter ever came into contact in deep space. A major breakthrough in antimatter research happened in October of the year 2017. Scientists at CERN, working on an experiment called BASE, made an incredibly precise measurement of the magnetic properties of the antiproton. They found that the magnetic moment of the antiproton was almost exactly the same as that of a regular proton, with a difference of only 1.5 parts per billion. This discovery supports the idea that the universe follows a fundamental rule called CPT symmetry, which states that the laws of physics should apply equally to both matter and antimatter. What made this finding even more significant was that it was the first time that an antimatter particle had been measured more accurately than its matter counterpart. Another exciting development in antimatter research took place in the year 2018. Scientists in Italy at the Positron Laboratory in Como successfully demonstrated antimatter quantum interference for the first time. This experiment, led by physicist Marco Giammarchi, revealed new details about how antimatter behaves at the quantum level. These findings could play a key role in deepening our understanding of fundamental physics. Antimatter is not just something found in deep space or high-energy physics experiments. It is also naturally produced on Earth in several ways. Some radioactive elements, like potassium-40, naturally release positrons as they decay. In addition, When high-energy gamma rays interact with matter, they can create positrons. Another antimatter particle, called an antineutrino, is formed through a different type of radioactive decay known as beta decay. Cosmic rays, which constantly hit Earth's atmosphere, also contain small amounts of antiparticles. A particularly surprising discovery came in the year 2011 when researchers found that antimatter is being created in Earth's own atmosphere. Scientists from the American Astronomical Society discovered that thunderstorms can produce positrons. This happens when the intense electric fields inside storm clouds accelerate electrons to nearly the speed of light, leading to bursts of gamma rays. These gamma rays then collide with the atmosphere, triggering the creation of antimatter. This unexpected finding showed that even everyday weather phenomena under the right conditions can generate antimatter. Another unexpected source of antimatter exists close to Earth, in the Van Allen radiation belts, two massive regions of charged particles trapped by Earth's magnetic field. Scientists using the Pamela spacecraft discovered antiprotons in these belts, proving that antimatter can exist in stable forms even near our planet. Antimatter can also form in places where the temperature is extremely high. When temperatures reach a certain point, there is enough energy to create both matter and antimatter particles in pairs. Scientists believe that in the earliest moments of the universe, during a time called baryogenesis, matter and antimatter were continuously being formed and destroyed. However, today, the universe is filled almost entirely with matter, while antimatter is nearly non-existent. This strange imbalance, known as Baryon asymmetry, is one of the biggest mysteries in modern physics. Scientists suspect that this might be connected to a phenomenon known as CP symmetry violation, which has been observed in some interactions between subatomic particles. If researchers can figure out why this imbalance exists, it could help explain why the universe, as we know it, exists at all. Recent observations in space suggest that some of the most extreme cosmic events, such as the formation of black holes and neutron stars, create vast amounts of positron-electron plasma. These exotic antimatter particles are then thrown into space at extraordinary speeds, forming powerful energy jets that stretch across enormous distances. Each new discovery adds more pieces to the puzzle of antimatter, pushing scientists to dig deeper into its mysteries and uncover its role in the universe. In the year 2023, a team of scientists, mainly from the University of Oxford, achieved something groundbreaking in particle physics. They successfully created the first-ever electron-positron beam plasma in a laboratory. This achievement was made possible through a collaboration with CERN's High Radiation to Materials (HRMT) facility. What made this experiment stand out was that it produced the highest number of positrons ever recorded in a controlled environment. To make this happen, the scientists used a powerful proton beam from the superproton synchrotron. This beam had an energy of 440 billion electron volts and contained around 300 billion protons. The beam was directed at a special target made of carbon and tantalum, which triggered an intense reaction. This reaction created a massive particle shower, producing about 15 trillion pairs of electrons and their antimatter counterparts, positrons. The resulting beam was so dense that it was able to sustain plasma oscillations, a key characteristic of highly energetic particle interactions. But this was not the first major breakthrough in antimatter research. The existence of antimatter particles had been confirmed decades earlier. In the year 1955, two physicists from the University of California, Berkeley, Emilio Segre and Owen Chamberlain, made history when they discovered the antiproton. Their work was so important that they were awarded the Nobel Prize in Physics in 1959. An antiproton is a mirror-image version of a proton, except for one major difference: it carries an opposite electric charge. It consists of two up antiquarks and one down antiquark, whereas a regular proton is made of two up quarks and one down quark. Just a year after this discovery, in 1956, another groundbreaking find was made when Bruce Quark and his team identified the antineutron. This discovery took place at the Bevatron, a particle accelerator at the Lawrence Berkeley National Laboratory. Scientists did not stop there. They pushed forward and managed to create even more complex antimatter particles. These included entire antinuclei made up of bound antiprotons and antineutrons. However, the extreme energy levels involved in these experiments made it impossible to form full antimatter atoms, where positrons would replace electrons. Then, in the year 1965, researchers led by Antonino Ziccici at CERN took another leap forward by producing antideuterium nuclei, which are composed of an antiproton and an antineutron. Around the same time, another team of scientists at Brookhaven National Laboratory in the United States also observed antideuterium, confirming the findings. Decades later, in 1995, CERN made an astonishing announcement. They had successfully created the first atoms of antihydrogen, the antimatter version of hydrogen. This was done using a method developed at SLAC and Fermilab during an experiment called PS210. Led by scientists Walter Ohlert and Mario Macri, the experiment took place in CERN's low-energy antiproton ring. Not long after, Fermilab confirmed CERN's results by producing about 100 antihydrogen atoms. However, these atoms were extremely energetic, making them difficult to study. To solve this problem, two major research collaborations, Athena and ATRAP, were formed in the late 1990s. Their goal was to slow down and trap antihydrogen atoms, allowing scientists to analyze them in detail. Then, in the year 1999, CERN launched a new device called the Antiproton Decelerator. This machine was designed to slow down antiprotons from speeds equivalent to 3.5 billion electron volts to just over 5 million electron volts. Although this was still extremely fast, it was a huge improvement. 3 years later, in late 2002, scientists from the Athena project made history by creating the world's first cold antihydrogen. The ATRAP project reported similar results soon after. To achieve this, they used a special trapping method. First, millions of antiprotons were captured and cooled by passing them through a thin sheet of foil before being held in a device known as a Penning-Malmberg trap. However, the process was highly inefficient. Only about 25,000 antiprotons were successfully trapped out of an initial 25 million. Once inside the trap, the antiprotons were still too energetic. To cool them further, they were mixed with a plasma of electrons. The electrons lost energy through radiation, and in turn, they cooled the antiprotons through collisions. After this, the electrons were removed using electric fields, leaving behind extremely cold antiprotons. At the same time, a separate cloud of positrons was collected from a radioactive sodium source and stored in another trap. The positrons were then mixed with the cold antiprotons, and some of them combined to form antihydrogen atoms. However, because these atoms were neutral, they were not affected by the electromagnetic fields used to trap charged particles. Within microseconds, the antihydrogen atoms would collide with the walls of the trap and annihilate. Over time, scientists managed to refine their methods, producing hundreds of millions of antihydrogen atoms. In the year 2005, the Athena project ended, and some of its researchers joined a new initiative called the Alpha Collaboration, also based at CERN. Their main objective was to test CPT symmetry, a fundamental principle in physics that suggests matter and antimatter should behave in exactly the same way. However, in order to study antihydrogen in detail, scientists needed to find a way to trap it for longer periods. Unlike charged antimatter particles, neutral antihydrogen atoms could not be held using electric fields. Instead, researchers relied on the fact that these atoms have tiny magnetic moments, which allow them to be confined in a special type of magnetic trap called a minimum B trap. This method worked, and in November 2010, the Alpha Collaboration achieved something never done before. They successfully trapped 38 antihydrogen atoms for about 1/6 of a second. This marked the first time in history that neutral antimatter had been held in place. On the 26th of April 2011, scientists at the Alpha experiment made a breakthrough that stunned the scientific world. They successfully captured and held onto 309 atoms of antihydrogen, the antimatter counterpart of hydrogen. Some of these atoms remained trapped for as long as 1,000 seconds, which is roughly 17 minutes. This achievement set a new record, as never before had neutral antimatter been contained for such an extended period. This remarkable feat opened up new possibilities for studying the fundamental properties of antimatter. Since then, Alpha has been using these trapped atoms to conduct research on the spectral characteristics of antihydrogen, a key step in understanding how antimatter behaves. Fast forward to the year 2016, and scientists developed an advanced machine called ELENA, which stands for Extra Low Energy Antiproton Decelerator. This cutting-edge device was designed to slow down and cool antiprotons, reducing their energy to 90,000 electron volts, a level cold enough to allow precise study. ELENA operates by first accelerating antiprotons and then controlling their movement within a specialized chamber. This improvement means that more than 100 antiprotons can now be captured every second. Although this is a massive leap forward in antimatter research, the production of even a tiny amount remains extremely challenging. In fact, it would take several thousand years just to create a single nanogram of antimatter, highlighting the immense difficulty of large-scale production. The biggest obstacle to mass-producing antimatter is the limited supply of antiprotons. According to CERN, when their facilities operate at full capacity, they can generate 10 million antiprotons per minute. Even if every single one of these antiprotons were converted into antihydrogen atoms, it would still take an astounding 100 billion years to produce just 1 gram of antihydrogen. To put this into perspective, this is nearly 8 times longer than the entire age of the universe. Furthermore, CERN produces only about 1% of the antimatter that Fermilab does, and neither facility was specifically designed for large-scale antimatter production. However, according to physicist Gerald Jackson, current technology is already advanced enough to produce and capture as much as 20 grams of antimatter per year. The only problem? The cost is astronomical. Each facility dedicated to antimatter production would require a staggering $670 million per year just to operate. This makes antimatter the most expensive substance on Earth. The existence of antihelium was first observed in the 1970s during high-energy experiments in the Soviet Union, where scientists at the Institute for High-Energy Physics detected the nuclei of antihelium-3. Later, researchers were able to artificially create these antihelium nuclei by colliding atomic nuclei at extremely high speeds, allowing antiprotons and antineutrons to combine into antihelium. In 2011, the STAR experiment at Brookhaven National Laboratory announced an even more astonishing achievement: the successful creation of antihelium-4, also known as anti-alpha particles. Meanwhile, the alpha magnetic spectrometer aboard the International Space Station has, as of the year 2021, recorded 8 possible detections of antihelium-3. If confirmed, these findings could have profound implications for our understanding of antimatter in the universe. One of the greatest difficulties in antimatter research is storage. Since antimatter annihilates upon contact with ordinary matter, it cannot be placed in a regular container. Instead, scientists use specialized devices like the penning trap, which utilizes electric and magnetic fields to keep charged antimatter particles suspended in empty space. However, this method does not work for neutral antimatter, which requires a different kind of containment system called an atomic trap. In 2011, CERN scientists set a record by preserving antihydrogen for approximately 17 minutes. But the longest storage period for antimatter particles is held by the trap experiment, where antiprotons were contained in a penning trap for an incredible 405 days. In 2018, researchers proposed a groundbreaking idea: a portable antimatter containment device capable of holding 1 billion antiprotons. This device could then be transported to other laboratories for further experiments, potentially revolutionizing the way antimatter is studied. Producing antimatter is not just difficult, it is extraordinarily expensive. Back in 2006, physicist Gerald Smith estimated that manufacturing just 10 milligrams of positrons would cost around $250 million. That translates to an astonishing $25 billion per gram. In comparison, a NASA report from 1999 suggested that the cost of producing a single gram of antihydrogen could reach a mind-blowing $62.5 trillion. The reason behind these astronomical costs is twofold. First, only a tiny fraction of the required antiprotons are created in particle accelerators. Second, these same accelerators are in high demand for other scientific research, further limiting antimatter production. CERN estimates that so far, only 1/1000th of a gram of antimatter has been produced, an amount so minuscule that it could not even power a tiny light bulb. To put this into perspective, the Manhattan Project, the effort that led to the development of the first atomic bomb, cost around $23 billion when adjusted for inflation to the year 2007. That means it would be cheaper to build multiple nuclear bombs than to produce even a tiny fraction of a gram of antimatter. Given the extreme costs of making antimatter, some scientists are exploring whether it might be possible to harvest it naturally. NASA-funded studies are investigating whether magnetic scoops could be used to gather antimatter trapped in the Earth's Van Allen radiation belts or even around massive gas planets like Jupiter. If successful, this approach could drastically lower the cost of obtaining antimatter for scientific and practical applications. Despite the challenges, antimatter has some practical applications. In medicine, positron emission tomography, or PET scans, rely on antimatter to create detailed images of the human body. In this process, unstable atoms emit positrons, which interact with electrons to produce gamma rays. These gamma rays are then used to detect diseases such as cancer. Additionally, laboratory experiments have shown that antiprotons could potentially be used in a cutting-edge cancer treatment, similar to proton therapy, by precisely targeting and destroying malignant cells. One of the most exciting possibilities is using antimatter as a power source for interplanetary and interstellar travel. Scientists have proposed using antimatter to trigger nuclear explosions that would propel spacecraft at speeds far greater than conventional rockets. Because antimatter contains more energy per unit mass than any known fuel, it could allow humans to travel to distant planets or even other star systems far more efficiently than current technology allows. If matter and antimatter annihilation could be harnessed perfectly, the energy released would be unmatched. Just 1 kilogram of antimatter colliding with 1 kilogram of ordinary matter would unleash an explosion equivalent to 43 megatons of TNT, almost as powerful as the largest hydrogen bomb ever detonated. However, harnessing this energy for practical use is extremely challenging. When positrons and electrons annihilate, they produce pure gamma rays, which are difficult to control. When protons and antiprotons collide, they create a mix of energetic particles, some of which can be manipulated using magnetic fields to generate thrust. Scientists are still working on finding ways to make antimatter propulsion a reality, but the potential remains enormous. When charged pions break down, they produce two main types of particles. Around 22% of their energy is carried away by neutrinos, which are nearly invisible, ghost-like particles that rarely interact with anything. The remaining 78% of the energy goes into unstable particles called charged muons. However, these muons don't last long. They quickly break down into a mix of electrons, their antimatter counterparts called positrons, and more neutrinos. Interestingly, about 2/3 of the muon's energy gets transferred to these newly formed neutrinos. If we add up all the neutrinos' energy from the entire process, it turns out that roughly 74% of the original energy from the charged pions ends up being carried away by neutrinos in one way or another. On another front, scientists have long wondered if antimatter could be used to trigger nuclear explosions. Theoretically, if antimatter were to come into contact with regular matter, it would release an enormous amount of energy in an instant. However, a major challenge is that antimatter is extremely difficult to create, and even if we could produce it, storing it in large amounts without it annihilating itself is nearly impossible. As of now, there is no sign that producing antimatter in large enough quantities for such purposes will ever be realistic. Still, during the Cold War, the United States Air Force funded research to understand antimatter better. They explored not only whether it could be used to set off nuclear weapons, but also the possibility of using it as a direct energy source for an explosive device. String theory is a complex but fascinating idea in physics that suggests the tiniest building blocks of the universe are not just tiny dots, like traditional particles, but instead tiny vibrating strings. These strings move through space and interact with one another, and their vibrations determine the properties of the particles we observe, such as their mass and charge. If you look at a string from far away, it behaves like a regular particle, but up close, it is actually a tiny loop or strand. One of the most important predictions of string theory is that one of these vibrational states corresponds to the graviton, a particle believed to carry the force of gravity. Because of this, string theory is considered a possible explanation for quantum gravity, which aims to merge gravity with the strange and powerful rules of quantum mechanics. Scientists are interested in string theory because it offers a potential way to answer some of the deepest mysteries in physics. Over the years, It has helped researchers make progress in understanding black holes, the early universe, and even the forces inside atoms. It has also influenced mathematical research in unexpected ways. But the biggest reason string theory is so exciting is that it could be a theory of everything, a single framework that explains all the fundamental forces of nature, including gravity, electromagnetism, and the nuclear forces that hold atoms together. However, even after decades of research, scientists are still trying to figure out whether string theory truly describes the real universe or if it allows for too many possibilities to make clear predictions. String theory first appeared in the late 1960s as an attempt to explain the strong nuclear force, which holds atomic nuclei together. But when another theory, quantum chromodynamics, was found to be a better explanation, scientists set string theory aside. However, they later realized that string theory had unexpected properties that made it a strong candidate for explaining gravity at the quantum level. The first version of string theory, called bosonic string theory, only included one type of particle known as bosons. Later, the theory expanded into what is now called superstring theory, which introduced the idea of supersymmetry. This concept suggests a deep connection between bosons and another class of particles known as fermions. Over time, physicists discovered 5 different versions of superstring theory. But in the mid-1990s, they found strong evidence that all 5 were actually different perspectives of one larger theory, called M-theory, which requires a universe with 11 dimensions instead of the usual 3 dimensions of space and 1 of time. In the late 1990s, scientists also uncovered an important relationship called the anti-de Sitter conformal field theory, ADES-CFT correspondence. This discovery linked string theory to another major area of physics, quantum field theory, suggesting that the two could provide new insights into each other. One of the biggest difficulties with string theory is that scientists still do not have a complete and clear definition of the full theory in every situation. Another challenge is that string theory predicts a vast number of possible universes, making it difficult to determine which version, if any, matches our own. These obstacles have led some physicists to question whether string theory is truly the right path, or if too much effort is being put into an idea that may never be testable. In the 20th century, physicists developed 2 major theories that explain the universe. The first was Albert Einstein's general theory of relativity, which describes gravity and the structure of space and time on a large scale, such as planets, stars, and galaxies. The second was quantum mechanics, which explains the strange behavior of tiny particles like electrons and photons. By the late 1970s, these 2 theories were enough to explain almost everything observed in nature, from the smallest particles to the evolution of the entire universe. However, despite their success, there was a huge problem. These 2 theories do not work well together. General relativity is based on classical physics, while quantum mechanics follows completely different rules. To fully understand the universe, scientists need a quantum theory of gravity, but attempts to merge the two have faced major difficulties. String theory is one of the most promising ideas for solving this puzzle, but it is still a work in progress. String theory starts with a fascinating idea. What if the tiny particles we think of as mere points in space are actually tiny, vibrating strings? Instead of treating them as dots with no size, string theory imagines them as minuscule, one-dimensional threads that wiggle and dance in space. These strings can be either open, like a short line, or closed, forming a tiny loop. The way they vibrate determines their properties, like their mass, charge, and how they interact with other particles. From a distance, these vibrating strings appear just like the fundamental particles physicists already study, fitting into existing models of physics. But when observed on incredibly tiny scales, smaller than anything we can currently measure, they behave in a way that could explain mysteries of the universe. One of the most exciting possibilities is that one of these vibrational patterns corresponds to the graviton, a theoretical particle thought to carry the force of gravity. If true, this would mean that string theory naturally includes gravity, something no other major theory of physics has managed to do. Over the past several decades, physicists working on string theory have made a remarkable discovery. Different versions of the theory, which at first seemed separate, are actually connected through mathematical relationships known as dualities. These dualities show that what appears to be one type of theory from one perspective may actually be another type of theory when viewed differently. This realization led to the idea that all consistent versions of string theory might be part of a bigger, unified framework known as M-theory. However, no one fully understands what M-theory truly is yet. It remains a work in progress. String theory has also provided surprising insights into black holes and the nature of gravity. For decades, physicists have struggled with strange paradoxes that arise when trying to apply quantum mechanics to black holes. In the late 1990s, a breakthrough came with the discovery of the anti-de Sitter conformal field theory correspondence, commonly called ADES-CFT correspondence. This discovery linked string theory to other well-established areas of physics, helping scientists study black holes in new ways. ADES-CFT has even found applications in fields outside of gravity, such as nuclear physics and condensed matter physics, which deal with the behavior of particles in extreme conditions. Because string theory attempts to incorporate all the fundamental forces of nature, including gravity, it has been proposed as a potential theory of everything. Many physicists hope that if string theory can be fully developed, it will provide a complete explanation of the universe, including why particles have the masses and charges they do, how dark matter fits into the picture, and even how the early universe expanded. However, there are still major challenges. Physicists do not yet know whether string theory truly describes our universe or whether it allows for many different possible universes. One of the biggest difficulties in string theory is that it is not fully understood in all situations. The easiest way to study how strings behave is through a mathematical approach called perturbation theory, which works by making small approximations. However, this method does not reveal everything about string theory, and physicists do not yet know how to define the theory in its full form without these approximations. Another unresolved mystery is how string theory determines the vacuum state, the fundamental state of the universe. Without this knowledge, it is unclear how much freedom the theory has in shaping the universe we observe today. Some critics argue that these unanswered questions make string theory too speculative, while others believe it is still worth exploring. To understand where string theory fits into modern physics, it helps to look at quantum field theory, the foundation of particle physics. Quantum field theory is the mathematical framework used to describe elementary particles, treating them as excitations in underlying fields. In this theory, scientists calculate probabilities of particle interactions using a technique called perturbation theory, which was developed in the early 20th century by physicists like Richard Feynman. A key tool in this method is Feynman diagrams, which are drawings that help visualize how particles interact. String theory builds upon these ideas but makes a radical change. Instead of imagining particles as points moving through space, it describes them as tiny strings. In traditional quantum field theory, a Feynman diagram represents a particle's motion as a one-dimensional line. In string theory, this line is replaced by a two-dimensional surface, representing the path of a vibrating string. This shift changes the mathematics and could explain things quantum field theory struggles with, such as gravity. However, one major challenge remains. String theory does not yet have a complete definition beyond perturbation theory, making it difficult to answer all the questions physicists want to explore. One of the most important aspects of string theory is the scale at which it operates. The length of a fundamental string is believed to be around 1/10,000,000th of a trillionth of a meter, the Planck length. This is so unimaginably small that, at the scales we can observe in experiments, these strings would look like tiny points. Only at the Planck scale do the effects of quantum gravity become important, making string theory a candidate for explaining how gravity works at the smallest scales. Originally, string theory was developed as bosonic string theory, which focused only on bosons, the particles that carry forces like photons in electromagnetism. However, this version had serious problems, so physicists expanded the idea into superstring theory, which includes both bosons and fermions, the particles that make up matter like electrons and quarks. Superstring theory also incorporates supersymmetry, an idea suggesting that every force-carrying boson has a corresponding matter particle, fermion, and vice versa. There are 5 major versions of superstring theory: Type 1, Type 2a, Type 2b, and 2 types of heterotic string theory. Each version allows for different types of strings, and at lower energy scales, they produce different physical properties. For example, Type 1 string theory includes both open strings, which have loose ends, and closed strings, which form loops, while the other versions focus only on closed strings. In our everyday experience, we are familiar with three dimensions that define space: height, width, and length. These three dimensions help us understand the shape and size of objects around us. However, Albert Einstein's groundbreaking theory of general relativity introduced a mind-bending idea. Time is not separate from space, but is actually a fourth dimension. Together, they form what scientists call space-time, a four-dimensional fabric that shapes the very structure of the universe. In this model, gravity is not simply a force pulling objects toward each other, as Isaac Newton once thought. Instead, gravity emerges from the way space-time bends and curves around massive objects like planets and stars. Even though this four-dimensional space-time model does a great job explaining how the universe works, scientists often explore theories that involve even more dimensions. Sometimes adding extra dimensions makes complex mathematical problems easier to solve, helping physicists understand the universe more clearly. In fact, certain scientific fields, like condensed matter physics, which studies how materials behave, can be described using theories with just 2 or 3 dimensions. But what if the universe actually has more than 4 dimensions, and we just haven't detected them yet? Some theories suggest that extra dimensions might exist, hidden in ways we cannot easily observe. One of the most fascinating ideas in modern physics is string theory. This theory suggests that, at the most fundamental level, everything in the universe is made up of tiny, vibrating strings rather than point-like particles. However, for string theory to make sense mathematically, it requires extra dimensions beyond the 4 we experience. Different versions of string theory predict different numbers of dimensions. Bosonic string theory suggests that spacetime has 26 dimensions, while superstring theory requires 10 dimensions, and an advanced version called M theory suggests there are 11 dimensions. But if these extra dimensions are real, why don't we see them? One possible answer lies in a concept called compactification. This idea proposes that the extra dimensions are curled up so tightly that they are too small for us to notice. Imagine looking at a garden hose from far away. It might seem like a simple one-dimensional line, but if you get closer, you'll see that it actually has a second dimension, its circular width. An ant crawling on the hose would experience both dimensions, but from a distance they seem hidden. Similarly, if extra dimensions exist, they might be compacted into shapes so tiny that we don't notice them in everyday life. To accurately describe the universe using string theory, these extra dimensions need to be curled up in a very specific way. Physicists believe they must take the shape of a complex 6-dimensional structure called a Calabi-Yau manifold. This structure is named after the mathematicians Eugenio Calabi and Xing-Tung Yau, who studied its properties. Only certain types of Calabi-Yau shapes would allow string theory to correctly describe the fundamental forces of nature, including electromagnetism, the weak and strong nuclear forces, and gravity. Another fascinating way to think about extra dimensions is through something called the brain-world scenario. In this idea, our entire universe is actually a 4-dimensional brain floating inside a higher dimensional space. Imagine a soap bubble floating in the air. The surface of the bubble is like our universe, while the air around it represents additional dimensions we cannot directly see. According to this theory, particles and forces like electromagnetism are confined to our 4-dimensional universe, but gravity might be able to spread into the extra dimensions. This could explain why gravity is so much weaker than the other fundamental forces. It might be leaking into hidden dimensions. String theory also introduces the idea of duality, which means that seemingly different theories might actually be 2 sides of the same coin. One type of duality, called S-duality, suggests that a group of particles that strongly interact, frequently colliding and combining in one theory, can be described as weakly interacting, rarely colliding, in another theory. This means that complex physical interactions might have simpler explanations from a different perspective. For example, type 1 string theory is mathematically equivalent to another theory called the SO32 heterotic string theory through S-duality. Another type of duality, called T-duality, deals with how strings behave in compact extra dimensions. It suggests that if a string moves around a circular dimension of a certain size, It can behave exactly like a string moving around a much smaller circle. This means that a universe with large extra dimensions might be indistinguishable from one with very small extra dimensions. Type 2a and Type 2b string theories, for instance, are actually equivalent through T-duality, even though they initially appear different. Duality is a powerful concept that appears not just in string theory, but in other areas of physics as well. A well-known example is the AD-CFT correspondence, which links string theory to quantum field theory. This surprising connection has provided new insights into how particles and forces behave at the smallest scales. In simple terms, when two theories are related by duality, it means that if you transform one theory in a certain way, it will end up looking just like the other theory. Even though they appear different at first glance, they are actually describing the same reality using different mathematical languages. Another important concept in string theory is the idea of branes. A brane, short for membrane, is a multidimensional object that extends the idea of a point particle into higher dimensions. A zero-dimensional brane is just a point, a one-dimensional brane is a string, and higher dimensional branes are called p-branes, where p represents the number of spatial dimensions. These branes move through space-time according to the laws of quantum mechanics and can have properties like mass and charge. They also interact with fundamental fields, just like how charged particles interact with electric and magnetic fields. A special type of brane, called a D-brane, plays a crucial role in string theory. Open strings, strings with two loose ends, must have their endpoints attached to a D-brane. The D stands for Dirichlet boundary conditions, a mathematical rule that dictates how the strings behave. D-branes have been instrumental in discoveries like the ADAS-CFT correspondence, which has shed light on many mysteries in quantum physics.